Good afternoon. Respected head of the Department of Electronics and other faculty members at this Department of Cummins College of Engineering, and all participants coming across Nagpur and outside Nagpur. Very good afternoon to all of you. My topic of discussion for the proposed two sessions is about power amplifier. Basically, power amplifier we use everywhere, right from low frequency such as audio amplifiers to the millimeter wave frequencies, or beyond that also what we used to call it as a sub-millimeter wave. The poly part of any transmitter is power amplifier. The last block before any antenna is power amplifier. Similarly, we have other type of amplifier. You might have also noticed, which is the first block of receiver. Just after the receiving antenna, we have, sorry, yeah, that we explicitly call it as low noise amplifier. So these amplifier blocks are very important. One block is just before an antenna in case of transmitter, and second part of or second type of amplifier which you can find in receivers, which is the first block of receiver, low noise amplifier. Purpose of these two amplifiers are different, though it looks like they are amplifier, but what actually they do with your electrical signal is completely different. When it is the story about low noise amplifier, LNA should amplify the signal to optimum strength, and condition is that it should produce minimum additional noise during the operation. That is what the job of LNA. I feel fortunate enough doing introduction. Ma'am said that I was associated with Samir Chennai during my MTech project work. So I did a two-stage low noise amplifier for C-band applications. That was the start of my journey in the field of amplifier. So I'm not a power amplifier designer in my early days. Rather, I am LNA designer. Years later, I decided to go ahead in the journey of the same microwave amplifier design. And I come to know that all you will appreciate, all of the circuitries nowadays are getting shrinked. Everything is getting designed and developed in the form of integrated circuits. So actually there is no scope for a pure analog RF designer in the field of maybe mixer, oscillator, filters, or even amplifiers. So there was only one area which was still it is a gray area where we need very high power to be generated. What do I mean by very high power? High power I mean here the power range in kilowatts or even megawatts, 10 to the power 3 or 10 to the power 6. So where do we need such type of high power amplifiers? So we have commercial applications such as our mobile phones, BTS towers, where do we need LNAs and PAs, but they do operate at very limited power. But when it comes to your defense applications such as electronic warfare, radar, or satellite applications, because satellite, we generally use communication satellites, we put them in geostationary orbit. So geostationary orbit is almost 36,000 kilometers away from the Earth's surface. So in this case, those power amplifiers should be in a position to generate very high amount of power, more than few hundreds of watts. So that is the area where I don't mean that power amplifier, anyways you have to go and design something like this, which I'll be going to discuss about. You may have a couple of other people, Jayanta sir will be there, Asmita ma'am will be there, they will talk about the MMICs. Even in your yesterday's session, Gandhi sir might have touched upon the microwave integrated circuit design approach for 5G. Almost more than 90% blocks of RF transmitter and receiver are nowadays being replaced with integrated circuits. But the power amplifiers required for high power application, for high frequency, we have to go with the hybrid approach. What do I mean by that hybrid approach? I will go and discuss throughout my presentation. This is what the background which I just wanted to let you know about what we are going to discuss in this coming session. So, my sincere request to our audience, if you have any question or something which I could help, because I have traveled from Bangalore, if these 2 hours, if I could make some meaningful contribution to this program, I'll be more than happy. I don't want to present, let's say, whatever slides I have, maybe more than 100 slides. I don't want to cover all those slides, but this should be a two-way kind of a communication. You can request, see, we were discussing with earlier speaker also. You might have discussed something related to the antennas. I do work, let me tell you something about my current work domain in Tejas Networks. I have been involved in the development side for massive MIMO radios. So this is the current project, 64TR, 32TR, massive MIMO radios, which you usually see on your mobile towers. So Tejas is the only company who manufactures these radios, and they have supplied more than 1 lakh radios to BSNL. And recently, in 2 cities of India, BSNL has started 5G services. So I'm more or less inclined to antennas, but since it is a radio, I have been a part of doing some analysis in PAs and cavity filters also, which you might have not came across by the time, because cavity filters, no way we discuss or we study about the cavity filters, it is not part of our curriculum. So please feel free at any point of time, you can steer my presentation, and my again request is that please make upcoming 2 or 3 hours, whatever time we spend together, let's try to make it as fruitful as possible. Alright. So the title itself says that solid state. Solid state means what are the other options? Are there any other type of PAs where do we use something apart from solid state? Solid state we understand something which is being made up of semiconductors. Something like our BJT, FET, MOSFET, PHEMT, gallium arsenide based transistors, gallium nitride based transistors. All this comes into the category of solid state. But what else we can use as amplifier? Somebody from you teaches microwave engineering to bit students? Somebody? Yeah. So you might have come across the tubes, microwave tubes, right? Reflex klystron, two cavity klystron, then multi cavity klystron. What else we have? Reflex klystron oscillator. Then we have traveling wave tube amplifiers. You are there, right? Couple of more tubes to name: magnetrons, gyrotrons, cyclotrons, amplitrons. So many microwave tubes are there, but at least we teach reflex klystron oscillator, two cavity klystron amplifier, then TWTA. So let me take you to the TWTA. What is it is being made up of? TWTA. Do we use any solid state device? Answer is no. We don't use transistor, right? What do we use? We use a microwave tube, specially designed microwave tube. It is just a modified version of our earlier, what we used to call it as vacuum tubes only, yes. Modified version of vacuum tubes. There are certain limitations of these conventional vacuum tubes, then people have invented during the World War II. These all inventions in the microwave had happened around World War II only. Somewhere in Germany, UK, right? So these TWTAs are vacuum tube kind of a structure. What is problem with that? If you have to design a traveling wave tube amplifier, the first thing it is very large, its weight would be more. So what will happen? If you don't have any weight constraint, then you can go ahead with the TWP. Where do you have weight constraints? Any application? Let's say you have to design an amplifier of 30 dB gain, 5 dB of noise figure, 1 gigahertz of a bandwidth, center frequency of 3.5 gigahertz. Typical application. Where do we use? Let's say 500-watt amplifier you have to design. Application is what? DRDO, people will do that for defense and their missiles, right? Their radars. That is the first thing. There we don't have any space constraint because we are working on the land itself. At the same time, if you have to design a amplifier of, let us say, 20% of center frequency bandwidth, now I am talking in terms of percentage. 20% of bandwidth, output is 200 watts. And application is space application. Your satellite will sit in a, your PA will sit in satellite. The satellite will be revolving around Earth at 36,000 kilometers. So even few grams of weight will increase the entire satellite project cost by few tens of crores. So TWTAs won't be a smarter choice where in satellites, in space applications. Similarly, if you have radio something what we do for BTS towers, if it is your PA itself occupies more than 60% of space of your entire radio. And it consumes more than 40% power of your entire radio. So most power hungry and space hungry block is PA. So there we can't go with TWTAs. So we have to go with solid state, something which is designed with the transistors. Will it take some time to load? Alright, so let's keep it as simple as possible because I could see after a very delicious lunch, you may feel little. So let us take a pause of few seconds and start. Are you following me? How many of you? Really? Very happy. So I had a limited lunch because I have to keep you awake. And when I can keep you awake, if I am awake. So all of you, we all will say that I am awake. Please, I am awake. Yeah. All right. Thank you so much. You all are very senior to me. Please apologize if I do. But it is all to make the thing, these 2 hours, as fruitful as possible. That is the only my intention. So to tell you, see, PAs or amplifiers are too complicated. People used to say that अगर आपको PA डिजाइन करना है, amplifier डिजाइन करना है, तो आपको डिवाइस लेना है, नॉन-लीनियर मॉडल लेना है, सॉफ्टवेयर चाहिए, you have to do the load flow analysis, you have to do source flow analysis, you have to do the very tedious job of matching load flow design, then you have to go ahead and do the power sweep analysis, frequency sweep analysis, then actual PA design will start. After these many steps, actual PA design will start. What do I mean by actual PA design? कि आपने जो PA बनाया है, how it will operate if you apply some complex modulated real world signal. Then the story starts for non-linearity. It's all about non-linearity. So just make the note of this word. PA design is handling non-linearity. You will appreciate that why I am saying that PA design means handling non-linearity. If your amplifier will go into the non-linearity, then only it will produce some good efficiency. You have to run into compression. Now all these things will be bouncer for you. So please excuse me. You can pick the sentences in words in between at the start. First thing is non-linearity. Second thing, real world complex modulated signal. That is actually giving generation to this non-linearity. Third part is impedance matching. So let's keep it as simple as possible. Sorry. So the first takeaway from this slide, whatever amplifier you are going to design at RF, what actually you are doing? If somebody asks you, you have to design, let us say, microwave amplifier. I'm not saying low noise or high power, class A, B, whatever it is, class E, F, whatever it is. If you are a microwave or RF amplifier designer, your life will move around this picture. This one, this one. So you have to design broadband, low loss, matching network. So what is the job of matching network? Why do we need it? Maximum power transfer, okay?
Impedance.
Yes. Whose impedance we have to match? We have a single stage transistor in between, maybe FET or BJT or HEMT, whatever it is. So what this matching network will actually do? It will match impedances. But whose impedances it will match? And once you match the impedances, maximum power will be transferred. So whose impedances it will match? It will match the input impedance of transistor with RF input impedance. So what is RF input impedance? It is 50 ohm. Everywhere we use 50 ohm as the RF impedance. There is a story behind this. Why 50 ohm only? To answer you quickly and maintain your interest, why 50 ohm? Somebody can comment. Why always RF impedance is 50 only?
Coaxial cable.
Coaxial cable, okay.
Impedance is
Coaxial cable impedance is 50 ohms.
no, 75 ohms.
75 ohms. Then, the reason is that it is a midway between power handling and losses. It is a geometric mean of 32 ohms and 75 ohms. It comes around 52 ohms. At that particular impedance, power handling would be maximum and losses would be minimum. That is why it is a universal value chosen for RF. I hope I could make some sense. Why do we use 50 ohm impedance? There is a graph. If you see in Google, you can see the power handling is maximum and losses will be minimum. So those numbers are 75 and 32. If you take mean of that, so you have optimum power handling and optimum power loss, or you can say close to minimum power loss. So that number is 50. Okay. So the first job, matching network 1 will match 50 ohms with whatever impedance we have at the input of this transistor. What will be that number? Somebody please. I mean, whether it is a real number or complex number. What do you mean by impedance? Is it a real number or complex number? But here it is V by I. Now you answer anything. Once you said that I am awake, for every question I will say that you are wrong. If you say real, answer will be wrong. If you say complex, wrong. Then you should be real awake. To answer, it can be both. Sorry. So impedance can be real because just now I said no. This 50 ohm is what? Real number. Here also it will be real number. But the story in between is complex. And what do we do? Here it will be R plus or minus Jx. Similarly, output impedance of transistor will be R plus or minus Jx. So now to make it as simple as possible, how can you make complex impedance with real impedance? How many questions we are taking out of a single slide? Please be awake. Are you getting something? Are you following me? So try to make as many questions as possible. Now, we know that the job of PA designer is, or any amplifier designer is designing matching networks. So what do you do when designing a matching network? You match complex impedance with the real impedance this side. You match complex impedance of output of transistor with the real impedance of output, which is 50 ohms. Then how do you do that? Can you match complex impedance with real part, real number? Can you match complex number with real number by some means?
By connecting capacitor or
Yeah, that definitely. We have to use some LC components or some microstrips. But I want the physics behind it. I don't want engineering as of now. No, try to follow what I am trying to take you to one direction. Definitely you are right. You are also correct. That is how we do the matching network. But what I am trying to make it apparent to all people sitting over here is that we are doing a simple thing. We are just matching 50 with some complex. So how can we do that? Let's say you have 10 plus J10. Can you match 50 with 10 plus J10? Again, both answers are valid. Yes or no? If you say yes, then how do we match? You first have to cancel out the reactive part. What is the reactive part? Plus J10. How do you cancel it out? You have to add minus J10. Then only plus J10 minus J10 will cancel out. And what is remaining over there? 10 only. Now both numbers are real, right? 15 and 10. Can you match it now? Can you match it now? How much time you will take? No. How much time you will take to match 50 ohms with 10 ohms? Do you need any tool? You have not given this thought, right? In just 10 seconds. You don't need any tool to match 50 ohms with 10 ohms. What is the formula? Huh? That we teach in microwave. Quarter wave line transformer, right? What is the formula for quarter wave line transformer? So the impedance of quarter wave will be under root of Z1 by Z2 square. So whatever impedance we have, let's say 50 ohm and here 10 ohms. So you have to take square and under root of that. Whatever impedance you will get some impedance number. So that will be the impedance of your quarter wave line. What do I mean by quarter wave line? Quarter wave means what? Length is lambda by 4, right? Quarter lambda by 4. So lambda is operating wavelength. So if you have a quarter wave line whose impedance is under root of these things, so it will match 50 ohms with 10 ohms. What do you have to do? You just have to take the output part, output impedance, put a lambda by 4 line, connect it to the 50 ohm, put transistor in between, bias it properly, your amplifier is ready. Isn't it simple? Are you following? You got the crux of PA design or any amplifier design? Yes or no? The biasing is totally different story. We'll touch upon it later on. Let's keep it because biasing is a DC part. RF is not going to interfere with your DC section. The whole job of DC bias is to take the required power to the transistor, voltages and currents, to act the transistor work into the active bias region. That is what we used to call as bias point at all. That is the only job of DC biasing network. Right?
So how just can you elaborate it? How we will have matching by connecting lambda by 4 line?
So you have to go for mathematical derivation. That is what I have asked you. If you teach the lambda by 4 transmission line, it is when I used to teach this, it is in unit number 4. It is there in Kulkarni or Liao, any book you can pick up and find out the impedance. The way you have the impedance equation for lambda by 4 line or lambda by 2 line, which is short circuited, open circuited. So if you find the impedance of lambda by 4 line, this will be the equation. So this is the first section impedance, this is second section impedance. I can show you once I open the tool. I can give any arbitrary numbers. Let us say 50, 10, 100, 10, 100,000, whatever it is. I will calculate that number. I'll put the impedance of that line. That line impedance should be that much. That is the lambda by 4 line impedance. And length will be always lambda by 4. It is independent of frequency. Means this design equation, is it dependent on frequency? No, it is not dependent on frequency. You can do at any lambda. You can do at any lambda. Okay. So something I was saying about, yeah, your job is done. You just have to design these networks. One type of matching network I have shown here. So your amplifier design will be finished here. Now you have to find the problem with this design. Criticize this design. What is the major problem of this matching network? What is the major problem of this matching network? The major problem is it will work best for one single wavelength. That means if you design at, let us say, 3.5 gigahertz, this will match 50 with 10 best at 3.5 gigahertz only. The moment you change the frequency, lambda will change. Lambda will change, its length will vary. Lambda by 4 will vary. So this is what? A narrow band matching network. Right? So what do you have to do to make it broadband? Let us pick the concept from our filter design. We have different LC filters, right? We have orders. Based on orders, our response will get changed. To get the sharp roll off, or we can say cut off, what do? We increase the filter order. Higher order filters we use. So similarly, multiple lambda by 4 lines can be connected in series to get the broadband response. That's it. This is what I am going to tell you for the rest of the time, but in some systematic manner. Please, if you have any question, feel free. Otherwise, we can move on the slides. Yeah, please.
What you said about the width of that line?
See, length is independent of impedance.
Yeah.
Width is nothing but impedance.
Okay.
Good question. The moment, let's say your length is 10 centimeters. So if you change the length to 11 centimeter, 9 centimeter, anyways that line is going to give you 50 ohms only. So you have correctly pointed out the design parameter. Width is going to decide the impedance. Larger the width of transmission line, smaller will be impedance. And smaller the width of transmission line, larger will be the impedance. So you can see different microstrip circuits where you see some minimum width, then width is increased. I show you in my design. So that is what the stepped impedance. Impedance is being changed in the steps. That is called as stepped impedance filter. So width is the parameter which decides impedance of your transmission line. Any other thing? Any other question? Okay, if no, let me now quickly move on. How much time I took for one slide? Half an hour? So now you please do the maths. I have 127 slides. So that we teach, Bhaskar sir, we teach velocity modulation, right? In microwaves we teach velocity modulation. So now I'll do some modulation, and you see that for next half an hour I'll try to go 50 slides. But I need your support. I'm not here to run the slides only. If I could make some transfer of information and get some questions which will trigger me to think, go back and rethink and come again with the proper justification, that would be worth. All right, so let's move on. Any further questions before I go ahead?
Sir, what is the thickness of
Thickness, okay. Thickness, see, if you take a microstrip, typically it is a 35 micron. Typically, it is 35 micron.
copper metal?
Copper.
And if we are using any other metal?
Metal, any metal you take, gold take, silver you take, but typically copper is being used as the conductor on your dielectric. So thickness, are you talking about the thickness of press or thickness of substrate?
It's metal.
A metal thickness typically 35 micron. See, there are 3 design parameters. To be honest, there are 4 design parameters for the designing of this transmission line. First is dielectric substrate whose epsilon r. We used to call it as a dielectric constant. If you are antenna designer, your dielectric constant requirement is different. And if you are a PA designer, your dielectric constant requirement is different. They will fight among each other, between each other all the time. Because in antennas we want intended radiation. So let us say if you have a dielectric substrate whose height is 2 mm and you have a dielectric substrate whose height is 10 mm. So can you answer which one is best for antenna? I have given you two substrates, sir. One whose height, dielectric height is 2 mm and number two, dielectric height is 10 mm. Which one will you choose and why for antenna design? Answer is, I will choose second one whose thickness is 10 mm and justification is because fringing fields will come out of those transmission lines and lie on your ground plane. The larger is the separation between top metal and bottom metal, more and more fields will come out of your press. And that is what radiation. So we want radiation losses as much as possible in antenna design. So the dielectric thickness will be more, that is the requirement for antennas. At the same time, for circuit design such as PAs and all, dielectric thickness should be minimum, which will result into the minimum radiation losses, and you will have a good low loss microstrip circuit. This is thickness only. If you take the epsilon r, dielectric constant, what is the requirement for antenna? What is the requirement for circuits? Because you want your antennas as small as possible, right? So what should be the dielectric constant? Lambda g is lambda 0 upon under root of epsilon r. Do I need to write that equation on the board? The conversion between guided wavelength, free space wavelength and epsilon r, relation among them. Lambda g is equal to lambda 0 upon under root of epsilon r. Higher epsilon r, lower lambda g. So smaller and smaller antennas we can design if you use high epsilon r dielectric substrate. So many design rules are there. So thank you for asking this design related question. Okay.
So this is on PCB or on semiconductor?
This will be on PCB. This will be microstrip PA. Okay. Yeah. Alright. So the same thing, as I said that now this was the crux of my presentation, the first slide only. The rest of the slides are going to elaborate the concept in systematic manner. If you could understand that slide or if you could follow that slide, then next subsequent slides will be very much easier for you. So what we do insert, we'll insert the matching network in between transistor, source is 50, load is 50, gamma in. Gamma itself is a reflection coefficient. Input reflection coefficient of transistor, we have to match with the source reflection coefficient of matching network. That is the design principle. Similarly, gamma out should be equal to gamma L. So that is how we design an output matching network. This is actual PA schematic you can see. We have a transistor in between. We place something, one transmission line here and one set of transmission line here, right? And this is just for the DC bias purpose. We have RF bypass capacitor, we have a resistor in between. Typically we put this resistor in RF PAs. We can use inductor or a lambda by 4 section transmission line here. What is the need of this? No, this we don't use for impedance matching. This lambda by 4 line has its own importance. Lambda by 4 line transfers the impedance. Let us say if you have a short over here, what will happen? I'll tell you. Just one story I'll tell you and we'll quickly move on. Your DC is coming from here, right? Let us say 5 volt is coming. If somehow some ripples are there in your source, some AC ripples, maybe in band ripples, lower frequency ripples or high frequency ripples, whatever it is. What will happen? Those ripples can flow till this point and they will interfere this RF line. This horizontal is RF line and these vertical lines are what? DC lines. So you have to be very careful. You have to separate DC from RF. If you mix them together, you will goof up. Your amplifier will not work as amplifier. What it will work as? Can you guess? If you have designed an amplifier and you have not taken care of these pandas, what will happen? Your amplifier will become. आपल्या मराठीमध्ये एक म्हण आहे. Many people are from Marathi background, right? मराठीमध्ये काय म्हणतात? करायला गेली मारुती आणि झाला गणपती. Right? So your amplifier will not become attenuator, it will become an oscillator. It happens. I was doing my MTech project long back in the 2008. I was doing PA. All of a sudden, it has got fabricated, and we got the good number of gain. My guide was very happy. She said that yeah, our amplifier is working. I said what's the great in that? We designed amplifier, it will work as an amplifier. That time I didn't have any idea. At the same time, some of my colleagues, they were from Crescent Engineering College, Chennai itself. They were also doing an amplifier. But they were doing power amplifier, I was doing low noise amplifier. And suddenly that girl came to me, we were having a tea break. I said that today we got tested our amplifier, it is giving some beautiful gain as per our expectations. She was a little nervous. She said that our amplifier is not amplifying anything. I said, how come it is possible? She said it is oscillating. That was the day. Then I started thinking about the transistor is there. In amplifier also we use transistor or not? In amplifier also we use transistor. So what is the difference between Maruti and Ganpati? The thing is that if you don't pay any attention to the stability, if you don't pay any attention between the DC and RF separation, your amplifier will start oscillating and it will become oscillator. So let me come back to this slide. I'm going very slow, please excuse me, but make sure that I finish all the contents which I have planned for. And on top of that, your coordinator requested me to say something. Even your earlier morning speaker said me something to discuss on hygiene for me. Oscars were also eager to have some discussion on that. So how you can increase my speed? Huh? You have to answer as fast as possible. If you don't answer, then I will take more time to be on that particular slide. Okay. So the DC signal, let's say some ripple is coming over here. That ripple should not come here. Means if this is the short point, what is the only solution? This point should be open for that ripple. And it can be done with the lambda by 4 line only. If you have a Smith chart, many of you might have used the Smith chart, right? What is the total length of Smith chart in wavelengths? If I start from here, moving like this and coming back to this point, what is the total length? Lambda by 2. This is short point, this is open point, this is Vmin, this is Vmax. So if I travel half of the Smith chart, I am transferring from short to open. If this point is short, if this point is short, if I put a lambda by 4 line in between, that lambda by 4 line will convert this point from short to open to this end for that ripple. So how beautiful lambda by 4 line is doing its job. Got it? Alright, so let's move on quickly. This is PA, no need to explain. We already know that this is the last block of any transmitter just before an antenna. Something in between you can find always with the choice of the band pass filtering. So depending on applications, we have different PA requirements. Somewhere we need higher efficiency, somewhere we need higher power, somewhere we need higher gain or output power something. So let's say our mobile phone application. What do we need here? Our battery should last long as much as possible. Maybe 10 hours, 12 hours. When it is possible? It will be only possible when you have a power amplifier who is higher in efficiency number. So that whatever DC you are giving, what is efficiency? Huh? Your DC power, how much portion of that DC power is being converted into RF output power? That is what efficiency. Higher the efficiency, batteries will long last. So depending on that, few applications you have higher efficiency, high output power, or broadband applications. Depending on that, you have to choose the PAs. So these are the typical microwave power modules wherein we use few stages of SSPAs, that means solid state power amplifiers. Then we have gain equalizers to stabilize the gain throughout the different PA blocks. And then we have main power amplifier, which is the TWTA, power booster or traveling wave tube amplifier. Then we have some management, power conditioners and control and command logics to switch on the transistor or some other components. So this is the typical block diagram of any microwave power module we use in defense applications. So these are some of the pictures of power modules. This is 50 watt, 25, 40 watt variant available for 10 to 12 gigahertz of band, 150, 200, 250. This is 3.2 kilowatt. So these are the amplifier modules which sits in radars or airborne applications. These are some of the other pictures for shipborne or airborne applications. On your flight also, fighter planes we have, there also we do have some transmitters and receivers. That is how they have been connected. Recently we all have witnessed Operation Sindoor. So how do we have controlled, or any army control, or any defense system, how do they control? They control with the help of nose, missile nose they used to call it as. So inside the missile nose we have microwave transmitters and receivers. Okay. Other concept, which is a parallel cascade. So if you have a requirement of, let us say, 250 watt of output power, if you put another transistor in series of this, what will happen? The next transistor will burn out because its maximum power handling will be 250 watt only. So what is the option? You have to connect them parallelly. So what will happen? Your input power will be divided into two parts. It will get amplified and again combined together and given the maximum output. Double of that will be given. So this concept is typically used in all microwave PA designs where you need very high power, called as cascaded power amplifiers. Alright? So even in PWTs also, you can see certain stages will be SSPS, pre-driver, driver, PA, then main PA. So 4, 5, 6 stages of SSPS will be there. Then you have a high voltage TWT, which will give you very high thousands of watts of output power. So this is the diagram. Any satellites in India, I made this when I was at ISRO. So this is how the chain of any power amplifier in satellites. It all starts with the gain block, typically 35 dB gain. Then we have digital phase shifter attenuator. Then we have DA means driver amplifier. DA1, DA2. Then we have three-way divider. So the signal coming from here will get divided into three parts, and you can see the parallel cascading, and they all will get combined through a three-way combiner, and you get the 150 watt of output power. The numbers and calculations all are written here. If you are interested, you can please refer to these slides. Devices also I have mentioned. So some of the designs I will share you with the particular these devices only. This is another lineup for earlier was 150 watt, and this is for 170 watt. Why I have picked up this number? I don't think I need to use mic, right? Am I audible till the first row? Should I continue using mic or I stop using it? Alright. So typically more than 150 watt is the power requirement of any traveling wave tube amplifier which we use for space applications. So the earlier topology for 150, and the second one is for 170, and the devices were different. If you see here, I have used CGH, 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 right? And here I have proposed with the TGF. So TGF, TGF, TGF. So TGF means Qualcomm, which is the world's leading manufacturer of these solid state transistors, and CGH stands for Cree. That time it was Cree in the year 2017. Now it has been taken up by MACOM. It's US based company. Okay. So these are the MMI CPAs. Here also you can see the parallel cascading approach, right? And the actual photograph of IC will look like this. It can work up to 230 gigahertz. Okay. So everywhere you find that different authors have proposed these topologies. So all they have used parallel cascading approach. Yeah, little bit minute details. So you can see here the matching network is the combination of transmission lines only. So these two transmission lines and this horizontal line, they are making up input matching. And these transmission lines are making up output matching, right? So this is how your PA design will look like. Some of the pictures, you just can have a look on this. So this is the first one. Author name is given at the bottom. This is broadband. Hope you appreciate now. You can see now the different width microstrip lines are being used here. Here width is different, here width is different, here different. Here also you can see transmission lines with different widths. So what is the purpose of that? It will offer a broadband impedance matching network. So it is a multi-octave bandwidth high power amplifier proposed by these authors. This is the design from ISRO. Again you can see the width is different here, width is smaller, again width has been increased, smaller width, likewise also. Now you can slowly start decoding the PA design, right? Somebody has given you this picture and have been asked you what are these widths are doing here. You can straight away tell that this entire portion is what? Input matching network. This entire portion is what? Output matching network. Why you have used variable widths? Because I just wanted to transfer this complex impedance to 50 ohm impedance. To do that job, I have used variable impedance microstrip sections. Right? That is what the job. And how do you do that? You cannot randomly pick up the width and length of these sections. You have to do the broadband impedance matching network design. Even you can put the L and C's over here. See, few authors have used the capacitors. That you can do. But using the capacitors and inductors well above 3 gigahertz is not possible. So you have to go ahead with the microstrip lines. Alright, so this is the actual block. This.
How to develop some design, how to finalize the leads, where, how much is required?
Definitely, that all comes from the Smith chart. I'll show you the actual design. So you can read, one book is there, I'll share that also if you are really interested. It all starts with the analog approach only. So you can correlate filter design with amplifier design. What is the difference between filter design and amplifier design? If you could correlate, then it would be decoded for you. If you cannot correlate the filter and amplifier, you will never realize the amplifier design. Now, sir's intention is that how do we decide this width and length of the microstrip line sections? So, what is the difference between this matching network design and filter design? The only difference is that in filter, we have 50 ohm at the source, 50 ohm at the load. We don't have variable impedances for filter. But what do we have for impedance matching? We have complex impedance here and real impedance of 50 ohms here. That is the only difference. So how do you tackle this? You have to normalize these impedances to one value. Do the design calculation. This is nothing but filter. Mind my words. Input matching network, output matching networks are nothing but filters. Yes. So you design filters. Just requirement is that your source impedance and load impedance will not be same. So all those concepts you design filter only, LC only. Then you transfer. Inductor is what? Series transmission line. Capacitor is what? Open circuited microstrip line. You replace. What is this? Can you guess? What is this? Or let me go back to more clearer picture so that I could make some sense. Yeah. Can you find inductors and capacitors in the matching networks on this picture? See, these are capacitors. This is also capacitor. This 50 ohm transmission line 2 is what? This is an inductor. So you can start with the lumped networks, but ultimately you have to replace them with the microstrip line. Open circuited microstrip line will act as a capacitor. Short circuited series transmission line will act as an inductor. So it is nothing but LC combination everywhere. You picked up any PA designer in the world, he will do this only. Combination of L and C to transfer the frequencies with minimum losses. That is the job of filter for given frequency.
Accordingly, impedance will be calculated and then accordingly width will get decided.
Sure, definitely. What is the bandwidth you need? Over the bandwidth, you first have to calculate what is your lower cutoff and higher cutoff for band pass filter. To be precise, these are the band pass filters. Input band pass, output band pass. Right? Let us say you are designing PA from 3.5 gigahertz. Bandwidth is from 3.4 to 3.6. Right? So this filter should transfer only 200 megahertz of frequencies. So what is this? This is band pass filter. So you first design band pass filter with LC and replace those inductors and capacitors with the transmission lines. And the width of length will be dependent on the substrate, what you have asked. The length and width, let us say you have 10 nanohenry of inductor and you have 10 picofarad of capacitor. How do you realize this on microstrip? You have to look for your stack up. What is the epsilon r? What is the dielectric thickness? What is the tan delta? Right? What is the copper thickness and frequency? Based on that, 10 nanohenry will be converted to some length and width of microstrip section. Similarly, capacitor will be 10 capacitor will be converted to some length and width of microstrip line specifically for that substrate. If you change the substrate, your length and width will vary. But the inductor and capacitor will be constant. Yeah, please, sure. Okay, so quickly move ahead. These are some of the surveys. Now, this is just the theoretical part, so let me skip this and go ahead. We have solid state power devices, power grid tubes, and EDVs, electron diode devices. So they have their characteristics. Very high power can be generated from EBDs, and all their lifetime and everything is being mentioned. So they can run for very limited lifetime because they work at very high power. And their voltage requirement is also like 2000 kilowatts. Okay. So based on your frequency and output requirement, you can choose between the different power devices available. But typically you can go ahead up to 10 gigahertz. You can use the solid state devices from this renowned industry. Some of them we have been used. I used for Cree, and here we have been using for MECOM also. Nowadays we use to call it as a MECOM and Quavo. Okay. So TWT and SSPA comparison is there. If you have requirement of very high power, you don't have any choice apart from TWT. But there is a memory effect which is being mentioned, so that something will be stored in the memory of your amplifier, so that it will affect on the performance of your SSPAs. So that we have to keep into mind. So in solid state also we have different technologies, right from silicon BJT to GaN HEMT. So GaN HEMTs are the only ideal candidates which can work at very high frequency. You may ask the question why? Answer is the band gap. Band gap between the valence band and conduction band is very high for gallium nitride semiconductor. Hence, they can operate at very high voltage and can produce very high power. So they are suitable for very high out power. So gallium arsenide are most suitable for LNAs, and gallium nitrides are most suitable for power amplifiers. So this is the maximum operating voltage. The higher the operating voltage, higher output power can be resulted. But the breakdown voltage you can see, that is another parameter which makes the GaN very much suitable candidate for power amplifier applications. Even power density is very high. But the noise performance of gallium arsenide is too good compared to gallium nitride. The worldwide market, you can see this picture, 2018 to 2028. So everywhere people are using gallium nitride. Some part of LDMOS is still there, but it will vanish out by the year 2030. This yellow color is LDMOS. LDMOS, I mean laterally diffused metal oxide semiconductor. So LDMOS transistors, slowly people are throwing them out and they are using gallium nitride as a semiconductor material. Next picture I will also tell you as per the application point of view. Mobile, defense, telecom and mobile is combined together in the green curve, aerospace and others. So you see everywhere the telecom and defense applications are more using the GaN devices. Okay. So this I have covered. Silicon they will have a handle very limited power. Silicon germanium combination what we do? Moving gallium arsenide we use. See, silicon and germanium itself are direct band gap semiconductors, and they are individual one. If you combine the third column and fifth column of your periodic table, something like gallium from third column, arsenide from fifth column, so it will become a compound semiconductor, gallium arsenide. Again, gallium from third column and nitride from fifth column, it will become gallium nitride. So these compound semiconductors will handle large amount of power. That is the inherent characteristic. So silicon and germanium, though their noise performance is good, but they are not good choice for handling high power. They will not withstand with such a high power. Okay, so these are the advantages. High operating voltage, high current density, high frequency makes gallium nitride ideal choice for high power applications. Rest of the properties or the electrical performance parameters are given for silicon, as rightly you were pointing about. You see, 1.11 is the energy gap between valence band and conduction band. So it cannot operate at higher voltage, but the gap between valence and conduction for GaN is 3.4. So it can operate for high voltage. Other parameter, the electric field, critical electric field, how many megawatt per centimeter the substrate can withstand. So it is pretty high as compared to silicon. So these two characteristic parameters are making gallium nitride is a natural choice for high power applications. Similarly, charge density, thermal conductivity, mobility, saturation. You see mobility. Highest mobility will offer by gallium arsenide. So can we use it for power applications? Answer is no, because for high voltage handling is the prime requirement. But you can use this gallium arsenide for high power. Higher frequency you can use it, sorry. For higher frequency, gallium arsenide can be used. But for high power, gallium nitride is the best choice.
From frequency point of view, it is almost 4 times.
4 times. So gallium arsenide based LNAs are the popular choice till last decade. That is what I said at the beginning only. Gallium
Now they are
arsenide.
not using gallium.
Now gallium nitride market has been jumped up. That is
But
why I
that-
showed these pictures.
But so now for higher frequency content in the school.
Yeah, gallium nitrides are using everywhere. They are using that. See, entire market is for gallium nitride only. Can you see the word here? Everywhere GaNs are coming. They are replacing your vacuum tubes. So there is no question of gallium arsenide and all. Everywhere you will find GaN. Even your mobile phones, few years down the line, they will use gallium nitride low noise amplifiers only. So this is another pictorial representation of these substrates and how silicon carbide and gallium nitride can be compared with all these parameters. Where thermal conductivity wise, silicon carbide is the best choice. Now the next possibility is gallium nitride on the substrate or silicon carbide. This whatever I am talking is about the device technology. So gallium nitride on silicon carbide will be the best choice for next generation high power applications. So you can see here material, possible substrate materials for GaN devices. But if you see the cost, GaN on GaN will be very high. GaN on silicon will be the best choice, whose cost is very low, but the frequency performance will be poor because silicon mobility you have seen. Alright. So please excuse me if I have skipped some of the minute details. Now these are some of the general comments which we have discussed. You can just go through this. Here is the last block. There are different classes, class A, B, AB, E, F, S, D, J, inverse J, whatever you name. More than 10 classes you will find. Then it should have maximum output power, efficiency, linearity are crucial factors. Bandwidth is important, reliability and lifetime is also need to be considered for PAs. Let's start the PA design. Now, total time I took since I started. Total time what I took? 1 hour.
1 hour.
I followed what I said. First slide 30 minutes. 50 slides I finished. Now, next 15 minutes, 50 more slides I can finish. That's not an issue, but whether it is making something, some information is being passed to you, or we can take a pause and let us have some discussion. I have covered there is so many parts we can discuss. But now let us come to the design. Now are you ready to start your design?
But it's the only power is the only reason for not using gallium. Band gap, that's it.
No, I showed you. Too many parameters, sir. If you compare silicon with all, not only silicon and GaN, I have given the comparison of silicon, gallium arsenide, silicon carbide, and gallium nitride. You see, this silicon is nowhere better in any performance parameter. You see,
Yeah, I'm talking about gallium.
gallium arsenide is only better in terms of mobility. Nowhere it is better than GaN or silicon carbide.
That let me bit show that also comes when we are designing microstrip line based passive components. We have designed it like power divider. So length and width we have followed some principle of we have provided the material. How that length and width
You have to calculate. I will show you a couple of examples.
that part
For given substrate, you give me the substrate. Dielectric constant, dielectric thickness, copper thickness, tang length. 4 parameters you give me, give the operating frequency, I will tell you for required impedance what should be length, what should be width. Or you can give me the length and width and substrate details. I will tell you what impedance it will offer. Other way also I can.
That part would
That tool is there. I'll show you definitely. Please remind me once I open ADS. I'll show you. Hope all of you are following and it makes some sense. So these are some of the parameters. Stability we have to check, otherwise what will happen? I said that phrase, no Marathi phrase. If you don't follow stability, it will become an oscillator. So what is stability? Output power, efficiency, linearity. Linearity we have ACPR, ACLR, EVM, error vector magnitude. All these things will be considered under linearity analysis. Then we have small and large signal gain. Small signal AC, small signal load line, large signal load line, something we teach in EDC, right? Small signal means applied signal is very small, and large signal means applied signal is very large in terms of power. For the benefit of audience, should I cover these things or directly jump on the design? Design only, right?
while designing it will get discussed.
Yeah, sure. Because I could see slowly one after another participant is moving out of the room. So I should not take you to their slides only. Because the moment you go inside, it will become more and more complicated. You have to pay your attention, you have to awake, you should not look into your mobile, then only it will make some sense. Otherwise, there is no sense in running the slides. So please excuse me if I am harsh at some point of a time, but I should not waste your time. If I am wasting, let me skip it and directly jump to the next. So how do we design PA? First we have to pick up the device. Device has to be picked up. Then we have to carry the DC analysis. DC analysis means I have to choose the operating point. Then we have to design a bias network. We have to go for stability analysis. Stability means that which I have skipped. What is the value of K? What is the value of delta? That we have to decide. Based on that only we'll understand this transistor will be stable or unstable for given frequency. So that is called as stability analysis. Then we have to design, we have to do node pool analysis. For what purpose? If you are following till this time, you will appreciate what is the meaning of this. Who will tell you the input impedance and output impedance of transistor? We said that design, we have to design a matching network. हमें मैचिंग नेटवर्क डिजाइन करना है. कॉम्प्लेक्स इंपेडेंस जो है उसको 50-50 के साथ मैच करना है. बट आपको कौन बताएगा कि कॉम्प्लेक्स इंपेडेंस कितना है ट्रांजिस्टर का? So that process is called as load analysis. Load pull means we vary the load and we see the power contours, gain contours, efficiency contours. अगर हम impedance को vary करते जाते हैं, so ये device हमारा कितना output power दे सकता है, कितना efficiency दे सकता है, कितना gain दे सकता है. So that impedance will pick and will start the design of matching network. Then complete amplifier का performance हमें देखना है. And finally we have to see the electromagnetic simulation, optimization. Then we have frequency sweep, power sweep, all these terms will come into the picture. Okay. So यही मैंने अभी बोला आपको, how do you determine the load impedance? There are whole lot of different options available. The best one, you go ahead with the non-linear device model, which will be provided by any manufacturer such as Macom or Qorvo. You take the non-linear model. I show you how to get the non-linear model, and that you have to use in your transistor. So to improve the efficiency and linearity, lot of work has been done in the literature. So all this first one, the name of science is Doherty. All these Doherty power amplifiers are used in base station applications. So they have very good efficiency for high PAPR signals. So please excuse me, I am not going into the details of all this stuff. So let me directly jump to the design as fast as possible. If you need a break, we can have 5 minutes of break so that we can get refreshed. Or if you don't need a break, those who are following, let's jump into design. It's up to you only. Okay. Continue. Okay. Now, if you have not followed anything, if you have not understood anything, that's perfectly fine. That's perfectly fine. Because I have been introduced the topic long back in 2008, it is almost end of 2015. You count down the number of years. Though I don't look like a 43 years old man, but I have spent half of my life in micro amplifiers. I'm not praising myself. I'm just trying to sit alongside you. You please don't feel that ये जो बकबक कर रहा है ये तो सारा जंप कर रहा है हमें कुछ समझ में नहीं आ रहा है. I could see the people sitting last row, and I can. We all are teachers, right? We could read the faces of people. समझ में आ रहा है? Many things are very difficult to understand, but to just make the tempo and what we can say, the set the tone, I have to cover right from the scratch. But if at least one or two people are able to follow, that is perfectly fine. Even if you have not able to catch up any statement out of my first star discussion, it is not good to affect for rest of the discussion. It is something like that. It is not like a daily soap. You have to watch the previous. No. Right? So please, I request you from bottom of my heart, please pay attention and start the fascinating field of PA design. Okay? So these are your specifications. You have to design amplifier at KU band. 11.2 GHz is your center frequency. Bandwidth requirement is plus or minus 100 megahertz. Means this should start from 11.150. 11,150 ते 11,250. Total bandwidth 100 megahertz. Got it? Isn't it simple? Then आपको output power चाहिए 5 watt. Minimum 5 watt. Now don't focus on this. What is PAP? Again, you will lose the focus. अरे ये तो मुझे पता नहीं है. Nothing but it is a peak in power. It is a power only. For you, first time you are looking at those specs, let us consider this as output power. Gain. It should be 7 dB. Greater than 7 dB at least. अरे यार, इतना सब बकबक करने के बाद क्या PA डिजाइन कर रहा है जिसका गेन 60 dB है? Throw it into the dustbin. All people will say that. What is the gain of your amplifier? 60 dB है, 6 dB है, 5 dB है. क्या काम का है? 5 dB गेन का एम्पलीफायर क्या काम का है? हमारे 6 dB का क्या काम है? Because we have not considered the operational compression region. This 7 dB gain is compressed gain. So some professor was asking me about the GAN and silicon. Now he is not here, so I would have continued that discussion. All these GAN PAs will always operate into 3 to 3 or 4 dB gain compression. 3 to 4 dB gain compression. Let's say you have a gain of 7 dB. If you make it uncompressed, your gain will be 11 dB. So it is actually 11 dB amplifier, but it is, why we are calling it as 7 dB? Because gain is compressed by 3.5 or 4 dB. फिर आपके मन में सवाल आता है कि भाई compress करना ही क्यों है? Why you are compressing it? So there are a whole lot of questions. So for that reason, you have to look back to this curve. Sorry, I am extremely sorry. This is what the compression. This is linear. This is 1:1 slope. You can see. Please try to follow me. This blue line is what? 1:1 slope. 1:1 means what? Input power is changed by 1 watt. Output power will also change by 1. That is what 1:1. If I say to this brown curve, it is a 2:1. So if input power is increased by 1 watt, output power will increase by 2 watt. That is called as slope 2:1. And the third one is input power increased by 1 watt, output power is increased by 3 watt. That is 3:1 slope. So why do we operate this? See, all linear amplifiers will operate like this only. Till this point we have a solid line. Till this point we have a solid line. Then we have solid line going down. We expect this should go like this only. This should go like this only, but it will never go, right? Because this is the point where your device limitation is going to start. Saturation, device will saturate and your output will not increase by same proportion whether it was increasing in the earlier region. So this region is called as a linear region. Next to that, this region is non-linear region. So all GAN PAs will work into this region. This is the 1 dB compression. 1 dB compression means you are expecting, let us say, 15 dB output, but you are getting 14 dB. Means your output is compressed by 1 dB. That point is a P1 dB compression. But we operate all PAs in 3 dB compression. So here we operate them in non-linearity. So this is the background to just to tell you about the gain concept. Okay, then input output return losses. S11, S22 should be less than minus 15. PAE at least 55%. Then efficiency also. I have skipped it. You have a whole lot of different efficiencies. Drain efficiency, total efficiency, power added efficiency. So which efficiency is most meaningful? Power added efficiency. What it considers? See, efficiency is what? Output AC power upon input DC power. Simplest way. But in case of low power, low frequency applications, we consider this as the actual efficiency. Output AC upon input DC. But in RF, you have seen that chain, right? Please excuse me, I'm going quickly back to that slide and I'll again jump back here. This setup you can see. Now if I have to calculate the efficiency of this stage, you see the gain here 8 dB, 7 dB, 7. If I have to see the efficiency for, let us say, for this stage, how do I calculate? I calculate the output AC power divided by input DC power, right? That is my DC efficiency. But where is this power you are considering? You are not considering 42 dBm means how much watts? It is more than 18 watts. You have to consider this input power. You are getting, let us say, 52 dBm output power. But when? आपको 52 dBm आउटपुट पावर कब मिलेगा? ऐसा नहीं होगा कि आप 0 dBm दे रहे हो और 52 मिल रहा है, कभी नहीं होगा. You have to add on the subsequent stages in between. So यहाँ पे आपका इनपुट 42 dBm है और आउटपुट 52 dBm है. तो आपको पावर एडेड एफिशिएंसी डिफाइन करना पड़ेगा आउटपुट एसी पावर माइनस आरएफ इनपुट डिवाइडेड बाय डीसी. दैट विल बी पावर एडेड एफिशिएंसी. वो खुद से 52 पे नहीं लेके जा रहा है आपको, उसको इनपुट में पहले आपने 42 दिया है. So this number has to be considered and that is called as no, never possible. So this is the typical efficiency. Output AC upon input DC. We used to call it as drain efficiency, collector efficiency, whatever, depending on the device. Power added. Output AC upon input AC. So जो मेरा 52 dBm है, उसमें से मुझे पहले 42 को subtract करना पड़ेगा. Then I have to divide it by DC power, and whatever number I get, that is my power added efficiency. Always power added efficiency will be less than drain efficiency or collector efficiency. Yeah, something else. It will never come to 100%. So that is not efficiency, that is gain. Output power upon input power, if you do the ratio, that will become power gain. That should be always higher. But it never the magic will happen. I used to consider, please excuse me, I used to discuss this topic with students when I teach EDC. See, you have amplifier whose input is 10 volt, output is 100 volt. From where you are getting this 90 volts? Is matching happening somewhere? No, magic is not at all happening. That extra 90 volt is coming out of your DC bias voltage. You have to apply the KVL to the output loop. What is that KVL? VCC minus ICRC minus VCE equal to 0. What is VCE then? VCE equal to VCC minus ICRC. Whatever VCC you have, now let us consider your RC is 0. The drop across collector resistor is 0. So maximum output voltage out of your transistor, which is VCE, can be, maximum will be VCC. Okay, so this is the device which I have used. It's a 5 watt device. GaN HDA. Sorry, these are the substrate details. Please excuse me. Dielectric constant, substrate thickness, loss tangent, copper thickness. You are asking something related to this. This is the thermal conductivity of it. And device I used, I have given the picture here. This is from Cree. This dice package I have used. 1, 2, 3, 4, 5, 6 pins to the input side, 6 pins to the output side. To be honest, मेरे पहले 6 महीने सिर्फ इसी में गए थे कि ये डिवाइस क्या है, इसको मैं सॉफ्टवेयर में कैसे यूज करूंगा, इसको अगर सॉफ्टवेयर में यूज करना है तो फिर इसका मॉडल चाहिए मुझे, हाउ डू आई गेट दैट मॉडल, एंड वंस आई गेट द मॉडल हाउ डू आई स्टार्ट विद द डिजाइन. So this is the model of transistor, of the same transistor. So I have set the Fed current tracer template available. I can show you in the tool itself. So first thing I will plot the DC input. So we know the load line. It is a graph between VC and IC for given VBE. Similarly, if it is a FET, then it is a graph between VDS and IDS for given VDS. So this is my A. If I bias the transistor here, this will operate in class A. This is cut off. So if I bias transistor at this point, it will become class B. If I bias in between of A and B, that will become class AB. So purposely I put the bias point close to the class B, so that this mode is called as D class B. Oh, sorry, D class AB. Okay. So this is stability analysis. So the K and delta values or stability factor we can see should be greater than 1. Now please don't ask me why greater than 1. Otherwise I will go back and start talking about the Smith chart and all the stuff. So just thumb rule, if the stability factor is greater than 1, it will not become Gantar. It will become amplifier only. So this is the gain what you can get, where it is S21. So the dB S21, dB S11, these are the results for bias network. Bias network means that drain and gate side line. So this is the step of load pull. From here you get the impedance. Can you see the number, complex number? So this you have to match with 50. Similarly, you should get one more number. That should be ZL. That again you have to match to the output load impedance. So this is here. Can you see this number? This is 40 minus J66. This is 7.5 minus J9. So what do? You will cancel out this part. minus 90 को plus 90 लगा देंगे, ये cancel होगा, इसको हमें 50 में ले जाना पड़ेगा. Similarly, इसको plus 66 लगा देंगे और इसको 50 में. अब ये जो relatively simple है. Translating 40 ohms to 50 ohms is simple. Than translating 7.5 ohms to 50 ohms. So that is the challenging part. So doing load pull analysis is the catch-all for PA design. The moment your impedances are close to 50 ohms, your design job will become simple. So make a note of this. अब ये PA का जो भी आउटपुट मैचिंग नेटवर्क होगा ना, वो बहुत आसान होगा. क्यों आसान होगा? क्योंकि आपको पता है आपको 40 को 50 बनाना है. 40 से 50 लेके जाना आसान है, लेकिन 7 साढ़े 7 से 50 लेके जाना बहुत मुश्किल है. So you will witness that the impedance matching network is real challenge for this PA. So these impedances I have marked here. Then I did some further tuning. There is a specific reason. I have tuned them because I know if this number has been jumped from 7.5 to 10, 12, that is okay for me. But at the cost of what? You cannot simply change these numbers and optimize. At the cost of gain. I am losing just 0.1 dB of gain. I am losing just 0.1 dBm of output power, and efficiency there is no compromise. So I can go ahead with these numbers also, so that this job can become little simpler for me. Then I did the matching network design. So this is input matching. You see the width is changing. So this is input matching, and this is just the response of matching network. And you remember this I did for KU band. So designer's life will be very, very complicated. Three requirements I have to meet: high power, high frequency, bandwidth. All these three requirements cannot meet simultaneously. So you see this response is very narrow band. And the gain is the function of the frequency. Still, I could achieve 200-250 megahertz of a bandwidth. Then you see how simple this network as compared to earlier picture. How many sections? 1, 2, 3, 4, 5, 6. 6 sections I have used for input matching network. And how many sections I used here? 1, 2, 3. The job will become very easy to translate any number which is closer to 50. And the response is also very nice. You see the gain variation. Right from 8 to 14 gigahertz, gain is varying less than 3 dB. Isn't it beautiful? But the same thing if you see in the earlier picture, gain is so sensitive with input matching network. You cannot separate the OMN and IMN. They both will contribute to the PA performance. Earlier you said that PA design means the design of OMN and IMN. Now I am trying to tell you that it is more about IMN. Right? Why? Because most of the GAN transistors in impedance will lie closer to 5 or 7 number of impedance. Whether output impedance will be close to 40, 35, or more than 30. Anything more than 25, 30 will be very piece of cake job for RF designer to translate it to the 50 ohm impedance. This is the layout. Somebody was asking, this is the actual layout. Here my transistor will sit. This is the bias network. Then something you can see here. What is that? That is radial stuff. If somebody is interested, I will say something on that. Otherwise, I have to move to the tool also. I have placed some tuning pads. Once it is being fabricated, if something is not working as per expectations, I can change the width. For those purpose, these tuning pads are being kept. This part I have not discussed anything. That is for stability improvement. LC combination is there. This is the small signal response of PA throughout 10 to 12 gigahertz. This is the input power versus output power. I'll show you all these results once I start my tool also. But just to make the continuity, let me show all these pictures. Input power in watts with respect to power adding efficiency. So power adding efficiency is not only the function of frequency, but also then this is the in-band response. Because we said that we want the center frequency 11.200 and it should work from 11.150 to 11.250. Still I have plotted from 11,100 megahertz to 11,300 megahertz. This is the band of 200 megahertz. Still you can see the output power delivered is more than 5 watt. Everywhere I could meet that. This is my threshold line, 5 watt. This left to y-axis is power delivered in watts. So everywhere throughout the band of 200 megahertz, output power is more than 5 watt. Gain, our design requirement was greater than 7 dB. So you can see this is the 8 dB threshold line. Throughout the band, gain is more than 8 dB everywhere. So this is how you see the performance in band. Similarly, I did for power delivered in dBm instead of watt, and the same gain on the other side. Yeah, drain and power added efficiency. As I said, drain efficiency is always higher than power added efficiency, but the more meaningful number is power added efficiency. So we should see we have met the target of power added efficiency more than 55%, but that is for very limited range. Even we met the drain efficiency only close to 55% for certain frequency, but rest of the things we could achieve more than 45% of, yeah, I'm right, 45% of power added efficiency throughout the band of 200 megahertz. Second design, more or less same, but the design will become simpler as you are operating at lower frequency 4 gigahertz C band. So quickly I will go through this. This is the device which I have used. The same steps: DC line, operating point, stability analysis, load pull, getting these numbers. Now you can see 2320. Similar job. So then translate it to some tuning values with some compromise in gain, output power, and PAE. You could see I could get 60% efficiency at low frequency. But when you go to the higher frequency, even 1 mm or less than 1 mm, you change your width or length, whole PA performance will move up. So see the beautiful response. Everywhere gain is flat. S11 is below -10 everywhere. So this is input matching. Similarly, output matching also very clean. Throughout the 2 gigahertz, I could get the S22 less than 10 dB. Gain is dying less than 1 dB only. Throughout 2 gigahertz of a band, 3 to 5. So one takeaway: designing power amplifier or any microwave circuit will be easy till 3, 4, 5 gigahertz. The moment you move ahead of that, your life will become complicated. Why? Huh? Answer is lambda. Higher the frequency, lambda will be smaller. Smaller lambda means any small changes in your microstrip transmission line length or width are going to affect on the impedance matching. This is the picture of C-band PA. These are the curves, gain, and return losses. Return loss we wanted to keep less than -10. So right from 3.4 or you can say 3.5 into 4.2 gigahertz or even 4.1 gigahertz, we could achieve the requirement of this one. Output power, again we could meet over the frequency, over the input frequency. PAE over the input frequency. This is output power in watts and gain in dB over the frequency. And in dBm output power, this is PAE and drain efficiency. You can see more than 60%. PAE we could achieve more than 60% for the band of 500 megahertz, which was the challenge for KU band design. Even we could not meet, even for 100 megahertz, we could not meet the requirement of PAE 50%. Here we could very comfortably meet the PAE more than 60% throughout the band of 500 megahertz. This is the real picture of the photograph which we have fabricated when I was at SAC. And there are real challenges. I have a couple of other stories to share with you. If somebody is interested, we can talk off the line. But getting it fabricated, I said before first 6 months, I struggled to understand how do I get nonlinear model and place it into areas and plot the GC analysis. But once I did that, then everything has started. But story has started over there. It has not ended. Until and unless I do not fabricate this, put the transistor, test in the lab, no one will appreciate. You could see my YouTube channel. People have commented that it's fantastic. This is something which I was looking since a long time. But could you please share the validation results? What is the real challenge to get it validated? First thing is this: you should get the PCB, you should get it fabricated. It is a very complex design. No one will give you the microstrip transmission line width less than 0.5 mm. That laser cutting machines you have, then only you can get the sharp edges and the minimum width which is required here. Smaller widths, 0.5 mm lines. Anything less than 1 mm, that PCB fabricator will not assure you. Because you all are doing antenna design, I am assuming that, so you will never come across this problem. So I paid 5,000 rupees to get it fabricated first time. Then what is the real challenge? Getting these L and C components to put here. 1, 2, 3 capacitors, 1, 2, 3 capacitors, one resistor here, one capacitor here, one resistor here, one capacitor here, another one here, and the major hero of this story, transistor. Can you guess the cost of this transistor for me? Just wild guess. अगर आपको पीसीबी बनाने में 5,000 लगे, ट्रांजिस्टर 100, 200, 500, 1000 ले लो, चलो खुश हो जाओ. The cost of transistor is up and above 5,000 for this design only I am talking about. If you go for KU band, C band, this was KU band, this is the C band, and if you go ahead for let us say 200 watt and 11 gigahertz, the cost of transistor is 25,000, 50,000, 90,000, 1 lakh. Still you will say that okay, you have grant like Kanchanman has got some support. So AICT, you ask AICT, you ask your college to get some 1-2 lakhs of fund. That is possible. Okay. Because you were in ISRO, so 1 lakh is not a big amount. Why you are telling stories? 1 lakh is not big amount for ISRO, agreed. Now story will start. The 200 watt transistor will be manufactured by a company called Quaro. These are the devices available in market. Sir, if you could pay attention now, I have surveyed all the devices present in the year 2007 to come up with my 150 watt output power PA design. These are the devices. In that range, you can see frequency range, gain, output power. I want at least 50 dB output power. So this I found, this is the perfect device. I started doing design. Quorum will not easily give you the non-linear model for this. First, you have to have a valid ADS. You should not use cracked one. If you have a pirated, they will not give a non-linear model. So you should have a valid tool license, you have to give the MAC ID of your tool where is your PC, where you will be using that software. Those things with your signature and your supervisor's signature, you have to submit to Quavo. They will review it and then only they will share you nonlinear model. You should work on that terminal only. Even inside SAC, if I do change my system, that model will not work anywhere else. Isn't it complicated? Somehow we got it. We got that model. We start working on that. So we designed the 200 watt. You see how complex the design. How many gates you have? You count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 16 pins for gate only. Transistor will have 3 pins, gate, drain and source. So they have a model who has 16 gate pins. You have to club all them together. Okay, the story I just park it aside for time being. You did everything. You got the non-linear model, you maintain the same PC, you have a valid radius license, you are ready to spend 1 lakh rupees. But still, Quaro have condition to sign a license form. They used to call it as license form. कि आप ये ट्रांजिस्टर लेके करोगे क्या? डिसाइन नहीं बनाओगे? इसको यूज कहाँ करोगे? Because this is very high power device. ऐसा नहीं मिलेगा मार्केट में. You have to sign license. किसको साइन करना है? ISR authority को साइन करना है या आप जहाँ भी काम कर रहे हैं. They have to sign it. This is such a niche device. They are not agreed to sign it. So we have not purchased this. But I have not stopped working on this device. I started working on this. I worked for a long. Then I did the same practice. Just for because my target was 200 watt, 150 watt. So 5 watt will not do anything. So we did for this is another problem. Because you had 16 gates, how many gates? 16 gates. So you will have 16 pins of actual transistor. Your transistor will be this much big. So how do you connect on PCB? You cannot connect single pin on microchip. How do you connect? So the concept is to use the bond wires, and these bond wires will be made up of gold. Sir, your gold comes here.
Yes, ma'am.
These gate pins, you have to use something called a bond wire. So that bond wire will be made up of a gate. And how do we model this bond wire? This is a 3D structure. ADS is a 2.5D software. So which software you have to use? Either CST or HFSS. To model the bond wire. What will happen if you change any parameter of this bond wire? Let's say its radius, its length, or its material. If you change it, its impedance will vary. Bond wire impedance बदलला, transistor का input impedance बदलला. Transistor का input impedance बदलला, matching network खलास. So that is the real challenge. So I did the study to calculate the effective inductance offered by the bond wire over the frequency. I calculated this in picohenries. So I did a lot of analysis for this because that was the only job I could do. So I did this. I proposed this 200 watt PA, something like this. I did parallel cascading. This is one stage. See, all the bond wires connected together. Input matching network, output matching network. But still it will not give me 150 watt. It will give me 90 watts. I will show you. Can you see here where is the power for 96 watt? How much I got out of single stage? 96 watt. But I want at least 150 watts. So what I have to do? I have to plug two stages in together parallelly. Sir, I will supply
Yeah.
मला सांगा किती आहे? Then I can just go. किती वाजले आता? 3:30 झाले ना? फारच फास्ट पळाले. Okay. So what I did, see. Let me go to the double stage. Yeah, I did this. So PA1, PA2, दोन्ही मी पॅरलली कॅस्केड केले. इनपुट मध्ये एक कपलर, आउटपुट मध्ये एक कपलर. Coupler you can use as a divider or combiner. Same coupler I can use at input and output. So first, but what is the requirement? This coupler should be wideband. So I designed a wideband coupler. This is very simple. Sir, you were asking something related to this.
Yes.
Basic passive.
Yes.
3 dB quadrature coupler I used in my project. So whatever signal you fed here, it will get divided into port 2 and 3. They will be 90 dB out of each other. And this port is called as isolated port. Ideally, zero power will come here. So this I used as a input and output. So this is the transmission line version of that branch line coupler. did in ADS. You can see the width and length. I calculated for given frequency and substrate. So this is the schematic response. This is the EM response. Schematic response ला काही होत नाही. आता सुद्धा मी काम करतो तेजस मध्ये because मी टीचर होतो जास्त वेळ. Whenever I do some simulations and give to my manager is Gopal Krishna Nayak. I'm very proud to work with him. So he used to say that Vivek, they used to call me VVR because there are 6-7 Viveks in Tejas. So I said, you please continue calling me VVR so there won't be any confusion. In my college also, people used to call me VVR. The moment I submit my schematic response, इससे कुछ नहीं होगा. I said, then I will go for EM. No, उससे भी कुछ नहीं होगा. You have to go in the lab and see the response. That is how the products will work. But for us, it is not possible कि हम जाए lab में पावर एम्पलीफायर बनाए उसको टेस्ट करने के लिए हमारे पास क्या है इलेक्ट्रॉनिक्स का सिरा तो छोड़ के कुछ नहीं है हमारे पास. Even in ISRO to get that tested, we didn't have a source. कितना पावर चाहिए था हमारे पीए के लिए. आप रियलाइज करो, आप एंटिसिपेट करो. मान लो लाइसेंसिंग भी हम साइन कर देते, हम वो ट्रांजिस्टर लेके आए 150 वाट वाला, उसको बना भी दिया. टेस्ट करने के लिए आपके पास क्या चाहिए? सोर्स चाहिए जिसका इनपुट कितना होना चाहिए. डू यू रिमेंबर द नंबर? व्हाट वाज द इनपुट फॉर माय पीए? 52 dBm is the output. Input was 42 dBm. Do you remember? अब 42 dBm पावर देने वाला सोर्स है क्या किसी के पास? उसको बोलते हैं पावर नेटवर्क एनालाइजर. वी नो वेक्टर नेटवर्क एनालाइजर. बट पावर नेटवर्क एनालाइजर बोल के इंस्ट्रूमेंट्स आते हैं जिनका आउटपुट पावर बहुत ज्यादा होता है. इसरो के पास इस समय एक इंस्ट्रूमेंट था जिसका आउटपुट पावर 23 dBm था. तो कभी-कभी ऐसा लग रहा था मैंने गलती कर दिया शायद ये टॉपिक चूज करके. Parallelly, I am trying to tell you a story and trying to tell you some technical information also. It was the moment my PhD guide, Dr. Anil Yuwale, said me that we can just wind it up, no problem, you make it broadband. We have sent paper to Singapore NTU, and that was a good paper, Scopus paper. Then you do two more Scopus publications and submit it. But I was working hard. I'll tell you, I am not praising myself. My daughter was just 1.5 years old. It was the story of 2017. My college sponsored me on full salary. Because of that only I could do something. If I would have been in the Shega, I have not done anything. My management, my principal, my head of the department, all colleagues, they have supported me. Without any extra faculty member, all my colleagues have managed my load for an entire semester. Whatever 15-20 load I had during that time. Then I realized that, but this realization has come after 3 months of a time. Because I didn't have that understanding. When I went in the month of May, मला वाटलं की मी पीए करून मस्त जाणार आता 6 महिन्यानं छान पेपर होईल पीएचडी सबमिट करू आता. 3 महिन्यानंतर लक्षात आलं याच्यात एवढा गोंधळ. मग आता काय करायचं? एक ऑप्शन उरलं की बॅक उचलून शेगावला वापस जायचं. एक ऑप्शन उरलं की जे आहे त्याला कंटिन्यू करायचं. Then I decided to continue. वापस जाऊन काय होणार आहे? इथे राहून जेवढं करता येईल तेवढं करत राहायचं. Your result will come after maybe 5 years down the line. We all believe in spirituality. We believe in good karmas. We believe in good deeds. We believe in past life. We believe in future lives. So whatever you do in your past life, it will come to you, even in this life also. Sorry, I'm taking you to the other direction. But that was, we also believe, we get the problems in our life, not only in education or profession. Then what is the solution? We have to surrender. So I surrendered. I said that I will just continue this. I will not skip it. Even my mentor at the SAC ISRO, she said that, आप रहोगे क्या? आपकी फैमिली है, फैमिली छोड़ के आए हैं, कॉलेज है, यहाँ इतने challenges हैं, 1.5 महीने में भाग जाओगे. I am not saying that I did something like a Guinness World Record. No. This is a common man story. Something like you and me only. But if it could make some contribution to your work, so it will be helpful. That is why I am sharing this. So I continued. We were not having that device. We were not having the source, nothing. But I did this thing. I written the paper, got accepted in NTU, that Nanyang Technological University, Singapore. So we have traveled to Singapore. Again, my college supported me. Half of that expenses college has beared, and half of that I have to manage. So it was almost 65,000 expenses. Again, because of good network, like I had network with Bhaskar sir. Before 24th November, हम दोनों एक दूसरे को पहचानते नहीं. 24th November को सुबह सर का फोन आया. Then we started and we have some connections. So the courtesy and hospitality he has extended. Thank you so much. So some part of a time, इसी दूसरे को मिल जाते हैं. So something, one of my friend is in Singapore. So he saved my 10,000 expenses. So I was उसी के घर जाके वही मैंने पेपर वगैरह प्रेजेंट किया. So this is how it happens. So then this entire paper we have published and I got the output power of more than 170. Everywhere you could see the output power is more than 170 watts. So at least this simulation, he is going to miss the climax of this picture. Now whoever will leave the lab will miss the climax. So please don't leave. I finish within few minutes. That was not the climax. That was just one hit. Climax will come in the year 2021. We are in 2017. Okay. So I did this, got this published paper. Okay. Everything is done. Compared this thing. Usually we do. So I have said that this is the best one by the time in the world. So then I got something testing problems and all covered. Okay, first let me, this I did in MATLAB to compare the radius and theoretical values. Then the performance variation with respect to the bond wire, that is all addition. कारण कुठलाही reference वाला आहे ना तो काय विचारेल तुम्हाला PhD मध्ये नवीन काय? What is your novelty? So this we have done to do the bond wire analysis. So these are the conclusions. We just read out these 4-5 statements. Mainly on this, any small change in the length of bond wire, equivalent inductance will change and it will affect on the entire PA performance. We only consider the length of the bond wire. However, radius we have not considered. That radius and height we have not considered. But can be other two parameters which will affect on the equivalent inductance and change in the PA performance. So should I tell climax now or go to the truth first? Climax, yeah. The climax is that it was year 2017. I came back. I was feeling, आता मस्त काम झालेलं आहे माझं. So I can finish it. But it was just 2 years of a time. I registered in January 2015. It was almost November 2017 I came back. So more than 2 years, close to 3. But still, university says that you have to, your counter should be minimum 3 years. Then only you can go ahead and submit. Then 2018 started. I was looking for Dover TP. This was general. This amplifier is called as a balanced power amplifier. दोन amplifier parallelly लावायचे. Input मध्ये 3 dB coupler, output मध्ये 3 dB coupler. त्याचा bond wire etc. ते केलं. But that is balanced amplifier. But I was looking for Dover T power amplifier. Dover T मध्ये काय झालं असतं जी efficiency मला 45% मिळाली आहे KV band. That I was looking for at least 50-55. And so that I could have some novel PhD work. So I worked for almost 6 months. So I could achieve some good results in the T also. But finally, I have not included in my thesis. Then 19 came, and we know what happened, right? So the whole world got stuck. So nothing we could do. Everything was stuck. So I have to wait. Then somewhere in January 2020, थोड़ा सुरू झालं सर. That time I submitted my thesis to university. परत ते second wave, third wave चालू होतं. So it took almost 1.5 years. I submitted in January 2020 and defense लागला 2021 च्या जून मध्ये. Meanwhile, then I started doing these activities, courses, workshop, YouTube वर टाकणं त्या गोष्टी. Now coming to the climax. 2021 ला झाला thesis. 2022 that playlist has become viral. So many audience have been connected through that playlist only. Then I delivered training to US-based students, Delhi University students. Some people are in Dubai also. There I discussed something related to the antennas, but somehow I got connected to the world through the digital media. And one fine day I got a call from Tejas. The engineer looked at my playlist typically for that PA design which I have discussed and asked me for a training. I delivered 10 days training, the story I discussed with Sir also, Milind Sir also. Then 10 days training, they found it useful and they decided that you can be a part of our team if you are wishing. So the 2017 dates fructified in the year 2022, no, 2023. I joined in 2023. So it happens. So maybe because of boring or some bouncers are coming, you may go out of the hall. That is your choice. I'm not saying that I'm expert of this. I'm a layman person. I'm learning RF. But proudly I can say I spent half of my life in the microwave designs only. Whatever ABCD, 1, 2, 3, 4, 5, I'm just crawling. I'm not expert like any other person. But the real challenges which we could face, that I try to share with you. Now, what is the plan in the remaining time is that we can have a couple of question answer session. We can go to the tool itself, wherein I will show you how this can be done. I have LDS in my system. Then, if you are done with the PAs, I have something other in my pocket, which is more fascinating if you could understand the language of antenna and if you are eager to understand the beam forming, that I can live demonstrate you how beam forming can be done. I can show you the microstrip antenna array and how the beam can be steered, or rather, what is actually the beam forming. That also we can do. I could see that in the morning you might have been discussed how dipole is going to radiate and all. This is not the right time to discuss all these things, but it is always there. You can please go and watch my YouTube if you are really interested. Even you all are expert guys. I am not saying that you go and watch. You can ask your students, those who are second year student, third year, final year. Even microwave series also I have. Microwave tools I have. Waveguides I have. Then this antenna, entire more than 12 hours training course I have using open source tool, NEC. I've conducted few trainings on NEC also, numerical electromagnetic code, monopole antenna, ground plane, dipole, everything I have tried to cover, right from the basic calculations, right from antenna parameters. And for this PA, everything you have, not only PA, right from ADS itself it is there. So you can please, whenever find time, please go to this. If you need, I just show you that playlist. And now it is up to the Bhaskar sir and Kanchanwal ma'am how do they would like to engage me for rest of the time, because I don't want to continue speaking too much, because I could see more than half of the people are being left. So I don't want to left you all.
Beam forming, can you show it?
Yeah, I'll be more than happy. You can ask me to be here till 10 p.m. also. But I don't want to force anything. That is what I am sorry for that. If you ask me, I can straight away go and tell you the beam forming. Beam forming directly.
5 minutes break.
Yeah, sure. You decide, sir. Now, please take a liberty. You tell me what to do. Whatever extent possible, I'll try to share with you. 5 minutes break. Thank you for all of you, those who are in the lab, and your patience listening and bearing me for more than 1.5 hours. Thank you. आणि माझे आणि मध्ये तर मॅथमॅटिक्स सांगितलंच आहे डिझाईन कसं करायचं सिग्रेट कसं करून ते सारखे आहे जास्त प्रॉब्लेम घ्यायचे तसं काही लिमिटेशन नाही दोन्हीची जीव आहे पण ऑलमोस्ट सारखे आहेत म्हणजे द्यायला जीएसटी फक्त थोडं स्वस्त आहे मला डे 9 ला गेले 2 सेशन पूर्ण डिफेक्टेड ग्राउंड स्ट्रक्चर पण ते सगळं एरियाज मध्ये आहे तुम्हाला सेम सीएसटी फक्त तुम्हाला टूल शिट नाही 15 दिवस 1 महिना आता तुम्ही जर ती लिस्ट पाहिली तुम्हाला वेळ असेल मला ज्यांना माहिती नाही मुलांना आणि ते बाहेर इनिशियली कलेक्टेड त्यांची कंपनी सुरू केली हा शिकावा पण माझं जास्तीत जास्त काम कारण एकट्याला हे शक्य नाही जोपर्यंत सपोर्ट नाही करणार तोपर्यंत तुम्ही काहीच नाही आणू शकत 2 महिन्यापासून किसानच्या लोकांना कळलं की हा कॉम्प्लिमेंटरी लायसन्स कारण हे तुम्ही पायरेटेड वापरून असं लेक्चर नाही घेऊ शकत आजही इथे करायचं होतं इट डिपेंड्स आपण कोणाला जास्त फोर्स नाही करू शकत सिस्टम आहे इथे जर एरियास राहिला असतं तर इथे सॉरी टू से पण लोकांची थोडी हे पाहिजे की इन्व्हॉल्वमेंट पाहिजे सॉरी टू से दादा तुम्ही सिनियर लोक आहे बरोबर आहे जर ते करायचं आहे तर कुठे क्लिक करायचं काय करायचं तिथून अडचण त्याला 2-3 दिवसाचा टाइम पाहिजे आणि थोडंसं बॅकग्राऊंड पाहिजे मग तुम्ही तिथे जाऊन त्या गोष्टी आता यांनी काहीतरी केलेलं आहे ज्यांचा आहे तुमचा एरिया कदाचित वेगळा असू शकतो त्याच्यात तुमचा आहे नसतो त्याला 2 तास पुरत नाही एक साईड अर्धा तास आणि 2 तासात तुम्ही किती हे करणार पण अल्टिमेटली तुम्हाला कनेक्ट व्हायला पाहिजे लोकांसोबत 2 तासात नाही मे बी लेटरवर तुम्ही कधी फोन करा मेल करा इन्फॉर्मेशन शेअर होतात माझे एक मित्र म्हणायचे हे बोलून सोपं आहे 10 बोलून नको
मला ऍक्च्युली त्रास खूप झाला पण त्याला डिटेक्ट केल्यानंतर त्याला ऍम्प्लिफाय करणं कारण नॉईज सिस्टम त्याच्यामध्ये मला इतकं भरपूर टास्क होतं माझ्यासाठी आता की सध्या मी एकदम म्हणजे माझ्याकडे काही ऑप्शन नाही होत आहे स्टील आय एम ट्राईंग की काय त्याचा करू शकतो ऍक्च्युली बॉडी ऑरावर काम करते फ्रिक्वेन्सी आहे तसं आपली बॉडीची जी फिटनेस आहे 520 हर्ट्जमध्ये एक्झॅक्ट व्हॅल्यू मला माहिती नाही पण तेच आता फाइंड आउट करण्याचा प्रयत्न करतो हेल्मेट टास्क होते की ॲम्प्लिफायर डिटेक्ट एखाद्या वेळेला ते amplifier बघा ना, personally खूपच म्हणजे मी पेपर्स पण पाहिले आणि कुठेही काहीही त्याचं
लोक काम करत होते.
काय करतात ते low frequency, typical low frequency नाही. Earlier photographs clearly captured the aura. You cannot measure it.
Immediate thought असा आहे तो मी देखील चुकीचा असेल मला तो. You can just frequency scale.
हां.
सुरुवातीला frequency scale करा आणि मग त्याला amplify करा आणि त्या signal ला पण discale.
Frequency scaling, amplification and discale.
म्हणजे मी एकदम चुकाही असेल बरं असं नाही म्हणत मी.
ठीक आहे ना, जर एक thought पण असू शकतो ना तो. म्हणजे त्या thought पण जर पुढे जाऊन मला
अल्टिमेटली तुम्हाला सिग्नलची स्ट्रेंथ वाढवायची आहे. मग कशी वाढवताय? फ्रिक्वेन्सी चॅलेंज आहे तर माझी फ्रिक्वेन्सी त्याची ट्रान्सलेट करून घ्या. फ्रिक्वेन्सी मल्टिप्लायर लावा. जर तुम्ही 10 हर्ट्झ वरून 100 हर्ट्झ वर गेले तर मग सुद्धा होईल.
त्याला डिटेक्ट पण करावं लागेल.
तुम्ही म्हणजे पूर्ण वेळ याच्यावर घालवा असं मी म्हणत नाही पण जस्ट एक मोमेंटरी थॉट
माझं
आला
आता होत तसंच आहे ना सर. हलवा पूर्ण वेळ मला
असं मी म्हणत नाही.
नाही
जर
पण
बेस असला मला तर मी म्हणलं असतं 100% वर तुम्ही असं करा. पण एक तरुण पाहायला हरकत नाही.
frequency scaling, then amplification.
फ्रिक्वेन्सी मल्टिप्लायर भेटतात. मला जर त्या फ्रिक्वेन्सीचा फ्रिक्वेन्सी मल्टिप्लायर भेटला
हां.
त्याला मल्टिप्लाय करा आणि ॲम्प्लिफाय करून द्या त्या फ्रिक्वेन्सीला. आहे 100 हर्ट्झ 200 हर्ट्झ जे काय
Actually, radio frequency imaging म्हणून एक डिव्हाइस आहे ऑरा स्कॅनिंग वाला. मे बी ते त्याला ऍक्च्युली ते डिव्हाइस असं सध्या माझ्याकडे न्यूजवरनं मागवलं त्याचा माझ्याकडे अवेलेबल नाही. पण दे आर डुईंग ऍक्च्युअली सेम थिंग कारण त्यांना जी फ्रिक्वेन्सी मिळते ती 100
तुम्ही अप्रिशिएट करायला पाहिजे मला.
वेगळं त्याचं मॅन्युअल मला मिळालेलं आहे. नाही नाही सर, मी तुम्हाला काय सांगू, मी जस्ट असं आजकाल असं माझं डोकं पूर्ण झोपेत काय उठेल ते मला सगळं ते सुचत असतं की मी आता कुठून काय करू शकते आणि कुठे आणि काय होतं ना असं जेव्हा आपण भेटत जातो आणि मला सगळे मूर्खातच समजतात ऍक्च्युली काही करते म्हणून असं काही होत नाही. स्टार्टिंगला येते मध्ये ते काय एंड मध्ये म्हणून मग माझं सध्या सुरू आहे. तर तुम्ही जो ऑप्शन दिलाय
तुम्हाला जे डिव्हाइस आहे त्याला इनपुट करायचं प्रयत्न करा.
पण त्याच्यासाठी तर ते 3 ते 3.5 लाखाचं डिव्हाइस आहे. सॉरी सर, मी थोडंसं तिकडे
मी हळूहळू एकेकाला बाहेर काढलं पण एवढी राहिले शेवटपर्यंत.
सगळे सिन्सिअर पार्टिसिपेंट्स त्यांना पण हेल्प होईल. त्यांचं काय प्रॉब्लेम स्टेटमेंट आता सरांचं तर त्यांना पीएचडी करायचं, सीओला रजिस्ट्रेशन करणार आहे. आणि बाकी तर सगळे आय थिंक पीएचडी होल्डर्स आहे. मॅडम पण पीएचडी आहे, मॅडम पण आहेत. तुम्ही आता रजिस्टर केली, तुम्ही केलाय करणार आहे सर. पण तुम्हाला चांगलं गायडन्स मिळेल म्हणजे एक प्रॉब्लेम स्टेटमेंट ला थोडंसं एक
मी सुरुवातीला म्हणेल की नाही हे खूप कठीण आहे तर मग ते पहिल्याच मोमेंटला उठून जाते.
जर तुम्ही जर जो कन्सेप्ट मला सांगितलाय ना तर त्याच्यासाठी तर मला ॲम्प्लिफायर पण अवेलेबल असेल. 100 सरांची तीच तर खासियत आहे, इझी टू टफ. असं बरोबर ते वन स्टेप बाय स्टेप घेऊन जातात. म्हणजे तुम्हाला लक्षातच येत नाही का आपण कारण त्याला इंटरॅक्टिव्ह होतं आणि खूप छान म्हणजे असं समजत गेलं ते. असं नाही म्हणणार 100% समजलं, पण 70% पर्यंत आम्ही ते ग्रास्प करू शकतो.
तुम्हाला एकदम प्रामाणिक मत सांगतो, मला त्यातला 100% कळत नाही. मला जेवढं कळतं तेवढंच बोललो. कारण तो टॉपिक त्याच्यात काही सुटलंच नाहीये. तुम्ही पाहाल स्टॅबिलिटी अनालिसिस पासून जर तुम्हाला फ्रिक्वेन्सी आणि पॉवर स्वीप करायचं आहे थोडं मी उघडून दाखवून
काल ऍक्च्युअली अनिरुद्ध सरांचं त्यांनी ना त्यांनी ते स्टॅबिलिटी हाऊ टू कॅल्क्युलेट स्टॅबिलिटी ऑन स्विच चार्ट त्यांनी ते काल घेतलं. त्यामुळे आज जेव्हा तुम्ही ते स्टॅबिलिटी बोलत होतात ना त्याचा आम्हाला थोडा बहुत
स्टॅबिलिटी मध्ये दोन आहेत.
अरविंद कुमार सर, अनिरुद्ध सर सांगितलंय. सॉरी अरविंद कुमार. आता हँडझॉन
3:30-4 वाजता
सकाळी जो बीम फॉर्मिंगचा
काय करतो 10 मिनिट फक्त हे दाखवतो इंटरनॅशनल हे आहे 10
हॅलो
Okay, welcome back. So, plan that next 20 minutes only. 5-10 minutes we'll spend on this BA, or maybe 5 minutes just, and the remaining time we'll spend on reform. So this is the tool ADS. You can see here. Also, Hindi okay, right? Hindi Marathi. So easy workspace आहे. Here you can see 4 gigahertz चा PA. Right? आणि डिव्हाइसचं नाव पण लिहिलेलं आहे CGH 4006P. ह्या सगळ्या स्टेप्स आहेत. सिस्टमॅटिक 1 2 3 4 5 6 7 8 9 10. राईट. फायनल स्टेप 10 आहे. मध्ये तुम्हाला कुठे 8 9 वगैरे दिसणार नाही. दॅट आय हॅव पर्पजली डिलीटेड इन बिटवीन मी जे अनालिसिस केलेलं आहे. पहिली स्टेप 1, लास्ट स्टेप 10. उलट जाऊया. फायनल स्टेप कडे पहिले जाऊ. आता हा एवढा छोटा झालेला आहे म्हणजे इकडेचे फॉन्ट आणि खूप छोटे. सो आय विल झूम इट अँड शो यू. दिस इज 50 ओम इम्पेडन्स. जे मी बोललो आहे तेच तुम्हाला टूल मध्ये दाखवतो. बाकी गोष्टींकडे जास्त लक्ष देऊ नका, अदरवाइज खूप कन्फ्युजन होईल. सो हा 50 ओम रेजिस्टर आहे असं कन्सिडर करा. सोर्स हे मॅचिंग नेटवर्क आहे. कोणतं? इनपुट मॅचिंग. आणि यालाच मी अटॅच काय केलेलं आहे? यालाच अटॅच केलेलं आहे डीसी लाईन. ही डीसी लाईन आहे. हा डीसी पार्ट इनपुटचा, हे इनपुट मॅचिंग नेटवर्क, हे आउटपुट मॅचिंग नेटवर्क, आणि हा ड्रेनचा डीसी बायसचा पार्ट. हा तुमचा पूर्ण पीए बघ केव्हा बनेल? जेव्हा तुम्ही स्टेप बाय स्टेप स्टेप 1 पासून सगळ्या गोष्टी करत याल. आणि हा इथे मध्ये यू कॅन सी ट्रान्झिस्टर CGH 4006P. याला म्हणतात नॉन लिनियर मॉडेल. हा जो ट्रान्झिस्टर दिसतोय दिस इटसेल्फ इज ओके. मग याचे रिझल्ट दाखवतो तुम्हाला.
सर त्याचा नॉन लिनियरिटी टेस्ट करून मग आपल्याला ठरवायचं असतं.
नाही. नॉन लिनियर मॉडेल का म्हटलं जातं सांगतो. शॉर्ट मध्ये, एकदम शॉर्ट मध्ये सांगतो. लिनियर तुम्हाला 1:1 स्लोप दाखवला, 2:1 दाखवला, 3:1 दाखवला. पण जेव्हा तुम्ही लो पॉवरला काम करता त्याच वेळेस ट्रान्झिस्टर लिनियर रिजन मध्ये असतात. हे सगळे जे पीएच आहेत हे सगळे नॉन लिनियर मध्ये काम करतात. मग लिनियर मध्ये ट्रान्झिस्टर वेगळं काम करतो. म्हणजे इनपुट पॉवर 1 न वाढवली तर आउटपुट 1 न वाढते, लिनियर होणार. इनपुट पॉवर 1 न वाढवली तर आउटपुट 2 न 3 न वाढते, म्हणजे नॉन लिनियरिटी. तर हे नॉन लिनियरिटी शो करणारे एक मॉडेल पाहिजे. अदरवाइज दुसरं मॉडेल असतं ज्याला डॉट एस टू पी फाईन.
नाही, तर आपण ट्रान्झिस्टर जेव्हा सिलेक्ट करतो तेव्हा तो ट्रान्झिस्टर नॉन लिनियर आहे की लिनियर आहे हे आपल्याला सिलेक्ट करायला लागतं का?
ट्रान्झिस्टर हा जर बेसिक म्हणजे आपण जर विचारलं कोणाला की ट्रान्झिस्टर लिनियर आहे की नॉन लिनियर आहे, तर आन्सर येतो बोथ.
हो, बरोबर आहे. पण मग त्याचं ते कोणत्या फ्रिक्वेन्सीवर तो नॉन लिनियरिटी दाखवतो आहे हे आपल्याला टेस्ट करायला लागतं.
फ्रिक्वेन्सीवर नाही, पॉवरवर. ट्रान्झिस्टर फ्रिक्वेन्सी डिपेंडेंट असतो. तुम्ही एकदम बरोबर आहे. बीजेटी जो फ्रिक्वेन्सीला काम करतात, टेलिव्हिटी, एचईएमटी, गॅस ते हाय फ्रिक्वेन्सीला करतात. पण जेव्हा लिनियर नॉन लिनियर आपण बोलणार, नॉन लिनियरिटी म्हणजे त्याला जेवढं इनपुट दिलंय त्याच्यापेक्षा काहीतरी एक्सपेक्टेड पेक्षा काहीतरी वेगळं बिहेव करणार, त्याला म्हणणार आपण नॉन लिनियर. म्हणून जर ते मॅथमॅटिकल इक्वेशन तुम्ही पाहिलं डिस्क्रिप्शन केलं आहे, हायर ऑर्डर प्रॉडक्ट्स e⁻², e⁻³ e⁻4 हे जे हायर ऑर्डर प्रॉडक्ट्स आहेत ते सगळे नॉन लिनियरिटी कॉन्ट्रीब्यूट करतात. फ्रिक्वेन्सी डिव्हाइसचा फ्रिक्वेन्सी ऍप्लिकेबल आहे. पण समजा 10 गिगाहर्ट्जचा डिव्हाइस आहे, तो काय 5 गिगाहर्ट्जला नॉन लिनियर होईल असं नाही. तो कामच नाही करणार 5 गिगाहर्ट्जला जर तो त्यासाठी बनलेला नाही. आणि 10 गिगाहर्ट्जचा डिव्हाइस 20 गिगाहर्ट्जला काम नाही करणार, तो त्यासाठी बनलेला नाही. हे कुठून आपण डिसाइड करणार? डिव्हाइस डेटा शीटवर एफटी दिलेली असते. एफटी म्हणजे अशी फ्रिक्वेन्सी की ज्या फ्रिक्वेन्सीला त्या डिव्हाइसची गेन 1 येते. डिव्हाइसची गेन 1 आली म्हणजे त्याला तुम्ही ऍम्प्लिफायर म्हणून तिकडे वापरू नाही शकत, तिकडे म्हणजे त्या फ्रिक्वेन्सीच्या पुढे. पण जर सेम फ्रिक्वेन्सी मध्ये आहे पॉवर तुम्ही एका लिमिटपेक्षा जास्त वाढवली तिथे तो नॉन लिनियर मध्ये गेला मग तुम्हाला त्याचे नॉन लिनियरच मॉडेल पाहिजे.
हा नॉन लिनियर मॉडेल आपल्याला घ्यायला लागतं.
मी सोप्या भाषेत असं सांगायचो मुलांना ईडीसी मध्ये सेकंड इयरची मुलं असतात फ्रेंडशिप होते आहे की नाही किंवा तू तुझ्या फ्रेंड सोबत वाटिका आहे शेगावमध्ये वाटिकेवर गेला आईस्क्रीम खायला तुला माहित आहे ते कसा फ्रेंड बिहेव करणार. ठीक आहे हे लिनियर मॉडेल झालं. नॉन लिनियर मॉडेल म्हणजे तू जर आनंद सागर मध्ये घेऊन गेला तर तुझा फ्रेंड कसं बिहेव करणार आहे तुला माहित नाही. वाटिकेवर घेऊन हे नाही समजणार की तू आनंद सागरला गेल्यावर काय करेल. सो लिनियर मॉडेल आणि S2P फाईल मधून तुम्हाला हे नाही समजणार की ट्रान्झिस्टरच्या नॉन लिनियरिटीला तो कसा बिहेव करेल. त्याला तुम्हाला नॉन लिनियर मॉडेलच घ्यावं लागेल. त्यामुळे सेम ट्रान्झिस्टरचा डिव्हाइस मॅन्युफॅक्चरर दोन फाईल देतो. एक देतो स्मॉल सिग्नल फाईल ज्याला S2P फाईल म्हणतात किंवा स्पाइस फाईल म्हणतात स्पाइस मॉडेल म्हणतात आणि दुसरा जो आहे तो नॉन लिनियर मॉडेल. जोपर्यंत नॉन लिनियर मॉडेल मिळत नाही तोपर्यंत डिव्हाइस वरून पीए डिझाइन तुम्ही करू शकत नाही. बरं मग काय करणार नॉन लिनियर मॉडेलच नाही मिळाला तर डॉट एसटीपी वरून पीए डिझाइन करू शकता. मग तुम्हाला फक्त स्मॉल सिग्नल गेन मिळेल म्हणजे S21 मिळेल लार्ज सिग्नल गेन मिळणार नाही. परत अजून वेगळं वेगळं.
ते नॉन लिनियर मॉडेल न येण्यामागे काय कारण आहे? त्याच्यात काय होतं?
हा बरोबर आहे. मला याचं उत्तर द्यायला खूप आवडेल. नाही विचारू द्या मॅडम. हा खूप महत्वाचा प्रश्न आहे. एकदम व्हॅलिड प्रश्न आहे. प्लीज मी एवढा हॅपी झालो की सरांनी हे विचारलं. मी काय बनवत आहे ट्रान्झिस्टर बनवत आहे. अरे मग तुला काय प्रॉब्लेम नॉन लिनियर मॉडेल द्यायला. देशकर सर डिझाईन करणार आहेत पीए करू दे. उद्या काय होईल मी त्यांना नॉन लिनियर मॉडेल दिलं म्हणजे मी त्यांना लिबर्टी देऊन टाकली. तुम्हाला पाहिजे तो पीए बनवा माझ्या ट्रान्झिस्टर पासून. बरोबर आहे. माझ्यावरची डिपेंडन्सी संपली. मी मॉडेल दिला नाही काय झालं तुम्हाला माहितच नाही या ट्रान्झिस्टर पासून ऍम्प्लिफायर कसा बनवायचा. मग मीच त्याचा ऍम्प्लिफायर बनवेल. मीच बटाटे उगवणार मीच चिप्स बनवणार आणि मग तुम्हाला देणार बटाटे देणार नाही. तुम्हाला चिप्स बनवायचे की काय बनवायचं पापड बनवायचे
म्हणून
फ्रीडम ठेवत नाही मॅन्युफॅक्चरर.
पण मग दुसरं कोणी ट्रान्झिस्टर बनवून देईल ना. मला समजा त्यांनी
माझ्यासारखे बटाटे कोणीच नाही उगवत तुझ्याला.
पण म्हणजे कसं आहे
दोनच मॅन्युफॅक्चरर आहे सांगतो मी क्री आणि मॅकॉन याच्या व्यतिरिक्त कॉर्नर आहे. बनवतो तुम्ही म्हणाल बटाटे उगवणारे खूप आहेत पण त्यांची मोनोपोली आहे सर. सगळं मार्केट तसंच चालतं. इलेक्ट्रॉनिक्सचं मार्केट असू द्या आपलं कन्झ्युमर मार्केट असू द्या काही असू द्या प्रत्येक जणांना आपली मोनोपोली केली आहे. बिझनेस स्ट्रॅटेजी. तेजसचा उद्या रेडिओ बनवायचा. रेडिओ बनवण्यासाठी त्यांना पीए पाहिजे. पीए बनवण्यासाठी ट्रान्झिस्टर पाहिजे. ट्रान्झिस्टर यूज करण्यासाठी त्याचं नॉन लिनियर मॉडेल पाहिजे. म्हणजे कंपनी काय करते अकॅडमिक्स मध्ये हा प्रश्न येत नाही. कंपनी म्हणते आमचा ट्रान्झिस्टर आहे हा आमचा इव्हॅल्युएशन बोर्ड आहे हा घ्या आणि अशाला असा तुम्ही तुमच्या फ्रिक्वेन्सीला स्केल करा. तुम्हाला हुशार आम्ही करणार नाही. तुम्हाला आम्ही टोपो बनवायला ठेवलंय. हे इव्हॅल बोर्ड घ्यायचं. इव्हॅल बोर्ड म्हणजे एक जनरल सर्किट बनवलेलं आहे. तेच तुम्ही घ्यायचं तसंच तुमच्या रेडिओमध्ये तुमच्या प्रॉडक्ट मध्ये वापरायचं. स्वतःहून इंजिनिअरिंग करायचं नाही.
इव्हॅल बोर्ड जर आपल्याला बनवायचा असेल वेगळ्या फ्रिक्वेन्सीसाठी
मॉडेल पाहिजे ना.
मॉडेल पाहिजे.
स्टोरी पूर्ण करून तिथेच येते. मॉडेल दिलं की त्यांचा इव्हॅल बोर्ड तुम्ही विकत घेणार नाही. त्यांचा इव्हॅल बोर्ड विकत घेणार नाही म्हणजे तुमच्याकडे जर 1 लाख रेडिओ बनवायचे आहेत तर तुमची प्रोजेक्टची कॉस्ट 500 करोड कमी होऊन जाईल. 500 करोडचं मार्केट जाईल त्यांचं. आणि उद्या तुम्ही स्वतः तुमचा पीए म्हणून दुसऱ्या छोट्या मोठ्या मार्केटमध्ये विकू शकता. ज्यांना त्या डिव्हाइस पासून लागणारा पीए पाहिजे तुमच्याकडे नॉन लिनियर मॉडेल आहे तुम्ही स्वतः फॅब्रिकेट करा मार्केटमध्ये विका. सो नो वन विल गिव्ह यू दॅट. बट स्टील काही लोक देतात. आता म्हणजे मार्केटमध्ये द्यायला पाहिजे पण काही मॉडेलचे अवेलेबल नसतात. मी दुसऱ्या भाषेमध्ये सांगितलं बट द थिंग इज दॅट ओनली.
पण ते मॉडेल एकदा मिळालं की मग आपल्याला ज्या स्टेप्स आपण बघितल्या किंवा ज्या तुम्ही सांगताय त्या अप्लाय करून पीए बनवणं हे काम बऱ्यापैकी
ठीक आहे. आता अजून त्याच्या आत जाऊन सांगायला लागेल. मी तुम्हाला मॉडेल दिलं पण ते मॉडेल किती दिलं आहे तुम्ही. आता हे मॉडेल बनवतात कसं त्यांच्याकडे एक लोडेबल मेजरमेंट सेटअप असतो, तिथे ते सगळे इम्पिडन्सेस चेक करतात, मेजर करतात आणि त्या मॉडेलमध्ये डंप करून स्पाइस मॉडेलच असतं, शेवटी त्याचा सिम्बॉल आणि त्याच्यामध्ये ती हिडन इन्फॉर्मेशन करून तुम्हाला देतात. जर मला हुशारी करायची आहे तर मी ते इम्पिडन्सेस चुकीचे देणार. मी सांगणार की हा डिव्हाइस 5 वॉटला पॉवर जनरेट करेल पण तो 4.5च करेल. त्यानं काय होणार, पीए डिझायनर चुकणार. मग तुम्ही काय म्हणणार, प्लीज रेफर टू अवर डेटा शीट अँड इव्हॅन बोर्ड. परत गोष्ट त्यांच्या R&D मध्ये येणार, दे विल डेव्हलप समथिंग, ते सांगतील की आमच्याकडे तुमचं पाठवा काय डिझाइन आहे, आम्ही मॉडिफाय करू अँड डोंट टास्क अस. डे टू डे बेसिसवर प्लीज, मी परत सगळ्यांना सॉरी म्हणतो आणि गोष्ट शेअर करतो. डे टू डे बेसिसवर मी वेंडर सोबत कम्युनिकेट करत आहे. वी आर डुईंग माय मोर रेडिओ, मी दाखवतो तुम्हाला. 3 वर्ष झाले आजपर्यंत अरे अँटेनाचं बेसिक मॉडेल काय आहे आमच्या वेंडरने कधीही सांगितलेलं नाही. मी तुम्हाला वेंडरचं नाव नाही सांगत, US बेस्ड कंपनी आहे, हा बिझनेस आहे सर. कोणी जर सांगेल, आता मी सांगून देतो कोणता आहे, प्रॉक्सिमिटी कपल्ड स्टॅक्ड पॅच अँटेना बनवला जातो. डायरेक्ट सांगून दिल्यानंतर तुमचं काम सुरू होतं, पण जोपर्यंत तुम्हाला माहितच नाही प्रॉक्सिमिटी कपल्ड अँटेना आहे, तुम्ही म्हणता इनसेट फीड आहे, लॅम्बडा कोर फीड आहे की अपर्चर कपल्ड फीड आहे, ट्रिबल पॅच आहे की नाही, तुमचा सिंगल पॅच आहे, ट्रिबल आणि रेडिएटिंग 2 पॅच आहेत का, सर्क्युलर आहे का, स्क्वेअर आहे का, 1760 प्रश्न राहतात. जर वेंडर सगळं डिस्क्लोज करून देईल त्याचा एक्झिस्टन्स काहीच राहणार नाही. सो मी आता रिक्वेस्ट करतो, प्लीज काही मध्ये विचारू नका. मला 4:30च्या आधी जसं मॅडमचं म्हणणं आहे तिथं मला स्टॉप करू द्या, देन आय एम अवेलेबल फॉर एनी वन डिस्कशन. सो क्विकली मी 5 मिनिट बोललो पण जास्त वेळ झाला. ओके, सो मी हे दाखवतो तुम्हाला, हा रिझल्ट दाखवायचा राहिला होता. सेम रिझल्ट इथे आहे आणि याच्यामध्ये होल लॉट ऑफ मॅथमॅटिक्स आहे. सगळे इक्वेशन प्लॉट केलेले आहे. एक जॉब कार्ड दाखवतो. हे असं जॉब कार्ड DXL फाईल असते किंवा गर्भ फाईल म्हणतात. ही फाईल आपल्याला PCB वेंडरला द्यायला लागते आणि ती असं आपल्याला PCB चे मी फोटो दाखवला स्लाइड्सवर तसं बनवून तयार करून आपल्या सबस्ट्रेटवर देतात. देन यू हॅव टू कनेक्ट SMA कनेक्टर्स, ट्रान्झिस्टर, इथे तुमचा LC, इथे रेजिस्टर, इकडे CCC, हा पूर्ण पीए तुमचा करून. ओके, सो आता 10 मिनिट आहेत माझ्याकडे. शुड आय गो टू मेन फॉर्म? So we have different servers at pages. So आता मी दुसऱ्या सर्व्हरकडे होतो, आता या सर्व्हरला आलोय. इथे आमच्याकडे सिस्टम मूव आहे. You can see we occasionally use other tools also. So let me go to system. तुम्हाला कोणालाही इथे मी सांगेल की जर कोणाला की साइट मध्ये काही पाहिजे आहे, EDS पाहिजे, EM2 पाहिजे, सिस्टम पाहिजे, तर ते टूल तुम्हाला मिळू शकतात. You can directly contact की साइट. तिथे माझं नाव मेन्शन करा, काही हरकत नाही. इमिडिएट तुम्हाला 2 दिवसात लायसन्स मिळेल, 1 मंथ इव्हॅन मिळेल आणि कंडिशनली जर कोणी स्पेसिफिकली त्याच्यात काम करत आहे तर 2-3 महिन्यासाठी पर्सनल रिक्वेस्ट करू शकता. सो यू कॅन गेट दिस टूल. आणि हे टूल भेटल्यानंतर जर तुम्हाला काही स्वतःचं डिझाईन करायचं आहे, मुलांना प्रोजेक्ट द्यायचे आहेत, तर यू कॅन रिअली स्टार्ट ऑन दॅट. जो काय सपोर्ट माझ्याकडून होऊ शकेल तो मी करेल. 2 तासात जेवढं पॉसिबल आहे मी प्रयत्न करतो. नाउ लेट मी टेक यू टू अँटेनाचे 2 प्लेन असतात, आपल्याला माहिती आहे. phi equal to 0, whether you understand or not, I am sorry to say this, but horizontal and vertical. Horizontal means azimuth, vertical means elevation. So horizontal म्हणजे see, it is a 3D radiation pattern. You can consider apple. ठीक आहे, म्हणजे याचं नाही, पण phi equal to 0 ला कट केला म्हणजे horizontal आणि phi equal to 90 ला कट केला म्हणजे vertical plane. आता हा जो सेटअप आहे हा मी स्पेसिफिकली हॉरिझॉन्टल प्लेन साठी बनवला. मायमो रेडिओ मध्ये काय, मायमो कावर म्हणतात, मल्टिपल इनपुट मल्टिपल आउटपुट. याच्यात बीम फॉर्मिंग होतं. मी माझ्याकडे प्रेझेंटेशन पण आहे, बट ड्यू टू टाइम कन्स्ट्रेंट मी डायरेक्ट तुम्हाला टूल मध्ये घेऊन आलो. इथे मी तुम्हाला आता बीम स्टीअर करून दाखवतो. हॉरिझॉन्टल डायरेक्शन 3GPP आहे का असेल तुम्ही, राईट? 3GPP यू हर्ड? 3GPP एक युनियन आहे, ITU आहे, ITU नंतर 3GPP आहे आणि ते सांगतं की काय स्टँडर्ड्सचे रेडिओज तुम्ही बनवले पाहिजे. 2G साठी काय स्टँडर्ड आहे, 3G साठी काय, 4G साठी काय, 5G साठी काय. तर 5G साठी 3GPP ने जे स्टँडर्ड दिलं आहे त्याच्यामध्ये जर मॅसिव्ह मायक्रोवेव्ह घेतला, हॉरिझॉन्टल बीम स्टीअरिंग पाहिलं तर प्लस ऑर मायनस 55 डिग्रीज तुम्ही स्टीअर करू शकता. समजा मी अँटेना आहे, सो दिस इज लेट अस से -55, दिस इज बोर साइड 0 डिग्री, दिस इज +55. ठीक आहे. सो असं मी मूव्ह करणार आहे. कोण? अँटेना. अँटेना आय मीन मेकॅनिकली अँटेना मूव्ह नाही करणार, त्याचा रेडिएशन पॅटर्न मूव्ह करणार आहे. त्याचा मेन बीम असेल, साइड लोब्स असतील, बॅक लोब असेल. So I will show you the radiation pattern which I can move from 0 to plus or minus any angle. Let us say आम्ही 45 पर्यंत करत आहोत, ±45 degree. You can ask me why 45 only. So there is justification. Similarly मी तुम्हाला वर्टिकल मध्ये दाखवेल की प्री-टिल्ट आमचा 60 डिग्रीचा आहे. 60 डिग्री पासून +5 आणि -5 म्हणजे टोटल तुम्ही किती झाले 2 झाले. 7 पासून +5 केले म्हणजे 12, 7 पासून -5 आले म्हणजे 2. म्हणजे ऍक्च्युअली वर्टिकल पॅटर्न तुम्ही कितीनं स्वीप करत आहे, 2 to 10 डिग्रीनं स्वीप करत आहे. So this is horizontal. You can see straight away I have steered this at 45 degrees. Can you see here? हा मार्कर मी टाकलेला आहे. कितीला आहे हा? 45 डिग्री. आणि हा त्याचा रेडिएशन पॅटर्न म्हणजे हे लोब्स आहेत. मला पहिले 3D दाखवतो बिकॉज यू पीपल लाईक टू सी 3D. आया स्टीयर झाला आहे पूर्ण. But 3D always difficult to understand. म्हणून मग त्याचा आपण 2D कट घेतो. So I have 2D कट. आता इथे पहा तुम्ही या बीमला मला स्वीप करायचं. लेट मी स्वीप इट. फर्स्ट मी त्याला काय करतो, प्लीज एक्सक्यूज मी तुम्हाला काही एक्सप्लेन केलं नाही. याच्यात कुठे अँटेना आहे, तुम्हाला पहिला याच्यात कुठे अँटेना आहे, अँटेना आहे याच्यात कुठे? अँटेना असल्याशिवाय बीम कसं येईल? हे जे तुम्हाला इथे दिसतंय ना, सिम्युलेशन रन्स, हे जे आहे दिस इज युअर आहे. कसला आहे आहे? मायक्रोस्ट्रिप पॅच अँटेना आहे याच्यात आहे. किती रोज आणि कॉलम्स आहेत? 12 रो आणि 8 कॉलम. म्हणजे कॉन्फिगरेशन काय? L×8. त्याच्यामध्ये स्पेसिंग अलॉंग x ऍक्सिस 48 mm, अलॉंग y ऍक्सिस 58 mm. आणि याच्यात मी अँटेना दिलेला आहे जो की HFSS मध्ये, CST मध्ये, ADS मध्ये, EM Pro मध्ये, CAD FICO मध्ये, IE3D मध्ये कशात बनवा तुम्ही. You can import that model here. These tools will talk to each other. Now you come to this and you will see the beam has been steered toward. आता मी तुम्हाला जर प्रश्न विचारला की बीम स्टीअरिंग आणि बीम फॉर्मिंग मध्ये काय डिफरन्स, सो ऑल ऑफ अस विल स्ट्रगल टू अंडरस्टँड व्हॉट इज डिफरन्स बिटवीन बीम स्टीअरिंग अँड बीम फॉर्मिंग. तर एकदम लिटरली तुम्ही शब्दशः अर्थ पकडला तर बीम फॉर्म करणे म्हणजे बीम फॉर्म. जास्त स्मार्टर टर्मिनॉलॉजी आहे बीम फॉर्मिंग. बीम फॉर्म करायचा म्हणजे तुम्हाला जनरेट करायचं आहे लिटरली, आणि स्टीअर करायचं म्हणजे जनरेट ऑलरेडी झालेला आहे. यू हॅव टू स्टीअर. सो द इंजिनिअरिंग बिहाइंड द स्टीअरिंग बीम इज व्हॉट. तुम्हाला काय करावं लागेल जर बीमला स्टीअर करायचं तर, यू हॅव टू फिट डिफरंट फेजेस टू ईच एलिमेंट. वेगवेगळ्या टाइमला सिग्नल तिथे आला पाहिजे प्रत्येक अँटेनाला, तर बीम स्टीअर होतो. आणि दॅट कॅन बी डन विथ फेजेस. ठीक आहे. सो मी तुम्हाला बीम स्टीअर करून दाखवला, 0 डिग्रीला दाखवला, 45 ला दाखवला. व्हॉट इज युअर ऑब्झर्वेशन? 0 डिग्रीला बीम पॅटर्न खूप क्लीन आहे. तुम्हाला ग्रेटिंग लोब्स माहित आहे? ग्रेटिंग लोब ऐकलाय तुम्ही? ग्रेटिंग लोब म्हणजे काय की हा जो लोब आहे याला साइड लोब म्हणतात, राईट? डीजीपीपी काय सांगते की तुमचा मेन बीम कितीवर आहे? मार्कर सिस्टम झालेले आहे माझे. मेन बीम कितीवर आहे? 26 डिग्रीवर आहे, राईट? 0.1 वर आहे, लेटेड बी 26 डिग्री आहे. तिथून किती डिग्री खाली तुमचा साइड लोब आहे? हे 7 आहे समजा. 23 minus 20, 26 minus 7 किती राहिलं? ऑलमोस्ट 18-19 dB तुमचा काय झाला, साईड लोब झाला. 3GPP स्टँडर्ड नुसार तो 13 पेक्षा बेटर पाहिजे. अदरवाइज काय होतं की मेन बीम मधली जेवढी पॉवर पाहिजे त्यापेक्षा पॉवर इकडे वेस्ट होतीये. दिस इज बेस्ट. मग तुम्ही हा जो पॅटर्न पाहिला हा खूप छान आहे, याचा एसएलएल खूप भारी आहे, 18 dB 4 राऊंड आहे. पण काही पॅटर्न असे असतात ज्यांचा एसएलएल जम्प करून जातो 12 dB 13 dB अँड दिस विल कम इनटू व्हर्टिकल प्लेन. हे पण तुम्हाला दाखवतो. ग्रेटिंग लोब मी सांगत होतो की हे जे लोब्स आहेत, हे लोब्स ग्रेटिंग लोब आहेत. हे तुमच्या जेव्हा तुम्ही बीम जास्त स्टिअर केला ना असा कॉर्नरला 45 डिग्री, तेव्हा ग्रेटिंग लोब वर आलेला होता. पाहिलं का? ऑब्झर्व केलं कोणी? 45 डिग्री मध्ये हा लोब खूप वर आलेला होता. मग तो काय करेल, या डायरेक्शन मध्ये जे युजर असतील आणि अनइंटेन्शनल युजरला कनेक्ट करून देईल तो लोब. मग त्यामुळे तुम्ही एका लिमिट पेक्षा जास्त बीम स्टिअर नाही करू शकत.
सर ते पुन्हा एकदा करून दाखवा.
दाखवता. माझ्याकडे सगळे इक्वेशन्स आहेत, सगळं इथे लिहून ठेवलेलं आहे, कॉन्सेप्ट आहे. प्रत्येक स्टिअरिंग अँगल साठी आधी मला फेजेस कॅल्क्युलेट करायचे.
अच्छा.
किती अँटेना एलिमेंट्स आहेत आणि त्या एलिमेंट्सला मला किती फेज द्यायचा आहे, त्यानुसार मग बीम कसा स्टिअर होईल त्याचं मॅथमॅटिकल इक्वेशन तुम्हाला माहित पाहिजे. ऑन पेपर तुम्हाला हे कॅल्क्युलेट करावं लागेल. जसे हा अँगल आहे, तुम्हाला हा फेज किती द्यायचा आहे. जर समजा तुम्हाला 7 डिग्रीला बीम 45 डिग्रीला बीम स्टिअर करायचा आहे, तुमच्या अँटेना मध्ये दोन अँटेना मधलं सेपरेशन किती आहे आणि ते कॉन्स्टंट असतं. मग दोन मधलं जेवढं आहे तेवढं सगळीकडे असतं, हॉरिझॉन्टल आणि व्हर्टिकल. हॉरिझॉन्टल साठी हॉरिझॉन्टल डिस्टन्स आहे, लॅम्बडा तुमची ऑपरेटिंग वेव्हलेंथ आहे. सो फॉर 45 डिग्री the difference spacing is this, so you get the phase number. That phase number you have to maintain and that is sequential phase. म्हणजे जर माझ्याकडे मी काय सांगितलं आर्किटेक्चर 1 2 असे किती आहेत, 12 आहेत. 1 2 to 12 12 रोज आहेत आणि कॉलम्स किती आहेत, 8 आहेत. हे माझं कॉन्फिगरेशन. याच्यामध्ये परत सब अरेचा कॉन्सेप्ट असतो. सब अरे म्हणजे हा टोटल अरे झाला, किती एलिमेंट झाले याच्यात, बारीसाठी 96 आणि प्रत्येक अँटेना ड्युअल पोलराइज्ड आहे, प्लस मायनस 45 डिग्री पोलराइज्ड. दिस इज प्लस 45 डिग्री पोलराइज्ड, दिस इज मायनस 45 डिग्री पोलराइज्ड. एका अँटेनाला दोन फील्ड लाईन्स आहेत, राईट. आणि समजा माझ्याकडे क्लब केलेला आहे मी 3x1 चा सर्व आहे. हे जास्त कॉम्प्लिकेटेड होऊन जातं, पण ऍक्च्युअल मध्ये किती आहे, 192 अँटेना एलिमेंट्स आहेत. हाऊ आय एम सेइंग 192, 12 8 आर 96. 96 फिजिकल अँटेना आहे, पण एका अँटेनाला किती पोर्ट आहे, सो 96 into 2 हाऊ मेनी अँटेनाज आय हॅव. ही लँग्वेजेस पहिले आपल्याला समजत नाही की काय म्हणत आहे. मी जर एखादा वेंडर मला 192 अँटेना एलिमेंट्सचा मॅसिव्ह मायनो अँटेना पॅनल देत आहे, तर त्याच्यामध्ये ऍक्च्युअल मध्ये फिजिकल अँटेना किती आहे, रो आणि कॉलमचं कॉन्फिगरेशन काय आहे, सब अरे काय आहे. सब अरे कॅन बी एनिथिंग. सब अरे कॅन बी एनिथिंग म्हणजे एनिथिंग मीन्स व्हॉट, आय कॅन क्लब 3 एलिमेंट्स टुगेदर अँड असाइन देम वन पोर्ट. 1 2 3 यांना मी एकत्र केलं, यांचा एक ग्रुप केला, याला मी काय म्हणालो, सब अरे. असे किती रो येतील, रो किती आहेत माझ्याकडे, 12 रो आहेत. 3 चा एक केला, असे किती येतील, बरोबर. हा पहिला, हा चौथा, असे 4 रो येतील. आणि एक सब अरेला माझ्याकडे एक पोर्ट पॉझिटिव्ह, एक पोर्ट निगेटिव्ह. ट्राय टू कॅच. एक पोर्ट पॉझिटिव्ह, एक पोर्ट निगेटिव्ह. किती सब अरेज आहेत एका रो मध्ये, तर एका कॉलम मध्ये 4 सब अरे. 4 गुणिले 2 8. 8 पोर्ट एका कॉलम मध्ये, टोटल कॉलम 8 8 8. या सिस्टमला काय म्हटलं जातं, लिटरली हे नाव असतं प्रॉडक्टचं. एरिक्सन पहा किंवा अजून तेजस पहा किंवा सॅमसंग नोकिया पहा, they are saying our massive MIMO radio 64T64R. What does it actually mean? We have 64 transmitters 64 receivers, but they are using the configuration like this. थोडंसं एक अजून कन्सेप्ट सांगतो. समजा तुम्ही सर्व्हर साईज चेंज केली, 3x1 च्या ऐवजी 6x1 केली. 6x1 म्हणजे 6 रो 1 कॉलम. टोटल किती रो राहतील तुमच्याकडे? आता 12x8 म्हणजे सर्व्हर किती राहतील? 2च राहतील. एकाला 2 म्हणजे एका कॉलम मध्ये किती कोड झाले? 4. 4 × 8 किती कोड झाले आता? एक्झॅक्टली. हे दोन प्रॉडक्ट आहेत तेजसचे सगळ्यात जास्त पॉप्युलर. 32T 32R मॅसिव्ह मायक्रो रेडिओ. दोन्हीचा आउटपुट पॉवर 300 वॉट 320 वॉट आहे. 32R मध्ये एक पॉवर एम्प्लिफायर 10 वॉटचा आहे आणि इथे 64TR मध्ये एक पॉवर एम्प्लिफायर 5 वॉटचा आहे. आणि पोर्ट कसे आहेत त्या साईडचो किती होतं तुमचं? 6 पंचे 30. 64 × 5 करा आणि 32 × 5 करा. दोन्हीचा आन्सर 32 × 10 करा. दोन्हीचा आन्सर किती येणार? बरोबर आहे ना? So this is the configuration how these systems will work. So sorry I am thinking something out of the scope. पण हे बीम फॉर्मिंग मध्ये सगळं हे आहे. So beam forming सबअरे कसा डिझाइन करायचा? 2x1 करायचा, 3x1 करायचा, 6x1 करायचा. त्यानं काय होतं? प्लीज तेच मी बोलत होतो. सबअरे का बरं चेंज करायचा? समजा तुम्ही बँगलोर मध्ये तुमची साईट आहे आणि एक साईट नागपूरच एक्झाम्पल घ्या. एक साईट कमिन्स कॉलेज जवळ आहे आणि एक साईड तुमची एकदम जिथे मोठ्या मोठ्या हाईट असलेल्या बिल्डिंग आहे. ठीक आहे. म्हणजे तुमचा जो युजर आहे तो हाईट वर आहे, तर तुमचा बीम काय पाहिजे? मोठा पाहिजे. त्याचा जो त्याची बीम विड्थ जी पाहिजे ती ब्रॉड पाहिजे. मग सबअरे साइज विल डिसाइड द बीम विड्थ. आय शो यू वन पिक्चर. ठीक आहे. सो quickly I show you vertical pattern. तुम्हाला परत एकदा 45 पाहिजे का?
हा, परत एकदा 45. त्याच्यासाठी तुम्ही डिस्टन्स सेट केला ना?
सगळं सेट केलं आहे पाहिजे. कॅल्क्युलेशन्स आहे.
हा.
I need 2 hours session for this.
ओके.
काही लोक म्हणत असतील बरं झालं. So I steered again to 45. Let's see whether we get it or not. 0 degree, sir. Mr. Sir.
Yes, sir.
Now we'll steer to some other angle, right? मी थोडं फास्ट केलं त्याला. इंटरनल माझं जे रिझॉल्युशन होतं ते 0.1 डिग्रीचं होतं. आता मी जे सेट हा जो रिझॉल्युशन आहे हा 1 डिग्री केला. त्याच्यामुळे फ्रॅक्शन ऑफ सेकंड मध्ये मला रिझल्ट येतो. नाव आय विल शो यू बोथ ॲट द सेम टाइम. मी म्हणलं ना तुमच्या लक्षात आहे का? लक्षात ठेवायचं काम नाही. You can see both the graphs here itself. हा जो आहे हा 0 डिग्रीचा आहे, राईट, सॉलिड वाला. आणि हा डॅश वाला जो ग्राफ आहे हा तुम्ही बीम जेव्हा 45 ला स्टीअर केला तेव्हा आहे. आता तुम्ही कंपेअर करू शकता दोन्ही. काय कंपॅरिझन दिसतं की जसं तुम्ही स्टीअरिंग केला बीम विड्थ, गेन, ग्रेटिंग लो, साइड लोब्स सगळ्यांवर इफेक्ट. सगळ्यात पहिले भाग गेन ड्रॉप झाले. असं केलं की मानेला ताणायचं सेम अनालॉजी आहे. जसा तुम्ही बीम टिल्ट केला किती डीबी डाऊन झाले तुम्ही, दॅट यू हॅव टू सी. आणि यू शुड नॉट बी लेस दॅन 3 डीबी. 3 डीबी म्हणजे आपल्याला माहिती आहे 3 डीबी डाऊन झाले म्हणजे हाफ पॉवर वेस्ट केली. सो जर तुम्ही 45 डिग्री स्टेअर केला आणि 3 डीबी गेन कमी झाली म्हणजे तुमची EIRP कमी झाली. EIRP मीन्स इफेक्टिव्ह आयसोट्रोपिक रेडिएटिव्ह पॉवर 320 तर 320च आहे. पण PT into GT, PT is the transmit power, GT is the gain of antenna. गेन ऑफ अँटेना 3 dB न कमी झाला म्हणजे ERRP तुमची हाफ झाली, 100 वरून डायरेक्ट 50 वर आली. दुसरी गोष्ट SLL खराब झाला, मोरलेस सेम आहे पण थोडा खराब आहे, कारण इथे पॉवर कमी आहे ना, ही पॉवर मायनस ही पॉवर म्हणजे डिफरन्स कमी झाला. तिसरी गोष्ट ग्रेटिंग लोड एकदम वाढून गेलं. हे पहा 0 डिग्रीला ग्रेटिंग लोड किती खाली आहे, पण 45 डिग्रीला ग्रेटिंग लोड खूप जास्त डॉमिनेट. This is how beam forming will happen.
हे सॉफ्टवेअर मध्ये झालं सर. प्रॅक्टिकली करताना हे आपण मग निदान प्रोसेसरला आपल्याला हँडल करावं, कमांड द्यावं.
दोन लेवलला काम होतं सर. पहिलं आहे तुम्हाला अरे बनवायचा आहे, अरे बनवल्यानंतर त्याचं पॉवर डिवायडर बनवायचं आहे, अनइक्वल पॉवर डिवायडर. तो एक फिक्स, त्याला बीम फॉर्मिंग मध्ये 3 टाइप्स आहेत, अॅनालॉग बीम फॉर्मिंग, डिजिटल बीम फॉर्मिंग, हायब्रिड बीम फॉर्मिंग. अॅनालॉग बीम फॉर्मिंग म्हणजे अॅनालॉग लेवलला बीम फॉर्मिंग होईल. तुम्ही ज्या पद्धतीने ट्रेसेस बनवणार, त्याची लेंथ जशी असेल, त्या प्रत्येक अँटेनाला जे जाणारा सिग्नल आहे त्याची फेज वेगळी होत जाईल त्या इक्वेशन वरून. 21 डिग्री, 42 डिग्री, मल्टिपल ऑफ 21, तसा तुम्हाला ट्रेसेस द्यायचे. दॅट इज कॉल्ड अॅनालॉग बीम फॉर्मिंग. डिजिटल बीम फॉर्मिंग जे तुम्ही बोलत आहे, FPGA मध्ये कंट्रोल करायचा पूर्ण, आणि ते जे नंबर्स आहेत ते डायरेक्टली तुमच्या अँटेनाला जातील. पॉवर डिवायडरचा काय मध्ये रूल नाही, पॉवर डिवायडर इक्वल पॉवर डिवायडर. आणि तिसरं कॉम्बिनेशन आहे ज्याला म्हणतात हायब्रिड बीम फॉर्मिंग. हायब्रिड बीम फॉर्मिंग दोन्हीचं मिक्सचर आहे. इनिशियली तुम्हाला एक प्रिंटेड घ्यायला लागेल, त्याच्यानुसार सबअरे डिसाईड करायला लागतील, त्यानुसार पॉवर डिवायडर, आणि मग दुसऱ्या लेवलचा कंट्रोल. म्हणजे इन टोटल जर तुम्हाला 21 डिग्रीचं फेज शिफ्ट पाहिजे, तर त्यातला काही फेज शिफ्ट तुमच्या अॅनालॉग मधून येईल आणि काही फेज शिफ्ट डिजिटल कंट्रोल वरून येईल. सो दॅट बीम फॉर्मिंग इज डिजिटल बीम फॉर्मिंग. इंडियामध्ये जनरली किंवा सगळीकडे जनरली हायब्रिड प्रेफर करतात, आणि फ्युचर 5G जे येणार आहे FR2, इट विल बी कम्प्लिटली डिजिटल बीम फॉर्मिंग. डिजिटल बीम फॉर्मिंग मध्ये काय होतं, शार्प तुम्हाला जेवढा फेज पाहिजे तेवढाच आहे. इथे तुम्हाला 21.5 डिग्री पाहिजे तर तो लाईन तुम्हाला 21 डिग्री देईल, 20 पाहिजे तर ती लाईन तुम्हाला 19.5 देईल. म्हणजे टॉलरन्सची लेवल खूप जास्त आहे. त्यानं काय होईल की तुमचा जो बीम स्टिअर होणार आहे त्याच्यावर त्याचा इफेक्ट होईल. मोबाईल आन्सर
CG साठी याच्यामध्ये काय ऍडव्हान्समेंट होतं?
5G ऍडव्हान्स पहिले येईल, 5G ऍडव्हान्स नंतर 6G येईल. 5G ऍडव्हान्स मध्ये सगळ्यात खूप छान प्रश्न विचारला. काही आय एम व्हेरी हॅपी मॅडम, या मॅडमचं लक्ष आहे. आय एम व्हेरी हॅपी की काही प्रश्न खरेच असे आले की ते वर्थ ठरले डिस्कशन मध्ये. हा एक खूप महत्त्वाचा प्रश्न आहे. पहिला नॉन लिनियर मॉडेलचा प्रश्न विचारला, आय एम व्हेरी हॅपी. आणि हा दुसरा प्रश्न की 6G काय होईल, 6G मध्ये काय होईल. आता मला सगळं माहिती आहे असं मी म्हणत नाही, पण जे काय रोजच्या कामात लक्षात येतं, 5G ऍडव्हान्स येणार आहे. 5G मध्ये काय होत आहे, सध्या 5G मध्ये काय होत आहे की जेवढे तुम्ही नंबर ऑफ अँटेनाज वाढवले, जेवढी फ्रिक्वेन्सी तुम्ही वाढवली, तुमचा बीम नॅरो झाला. बीम नॅरो झाला म्हणजे काय की तुम्ही काही रिजन तुम्हाला डेड स्पॉट मिळायला लागते. डेड स्पॉट म्हणजे त्या रिजन मध्ये 5G चा सिग्नल जाणारच नाही. समजा आता BTS टॉवर या साईडला आहे, BTS टॉवर आपल्या या साईडला असं कन्सिडर करूया. त्याचा बीम असा निघाला आणि हा 0 डिग्रीला, 0 डिग्रीला एवढा कॉर्नर तो कव्हर करेल, पण इकडे जो युजर आहे त्याला बीम मिळणार नाही. देन 5G ऍडव्हान्स आणि 6G मध्ये येणारा जो कॉन्सेप्ट आहे, स्टील इट इज अंडर हेवी रिसर्च. पण तुम्ही जर अँटेना मध्ये आणि मायक्रोवेव्ह मध्ये सगळ्यात जर महत्त्वाचा टॉपिक किंवा हॉटकेक ज्याला म्हणतात, दॅट इज RIS. RIS काही लोक IRS म्हणतात, रिकन्फिगरेबल इंटेलिजंट सर्व्हिसेस. सो तेजस हॅज डेमॉन्स्ट्रेटेड RIS. आता जे IMS झालं दिल्लीमध्ये, ते तेजसचं RIS डेमॉन्स्ट्रेट केलं आहे. तुम्ही पाहाल IIT बँगलोर, IIT जोधपूर, IIT भिलाई, तेजस नेटवर्क्स, TCS, कॉमेट ऑर्गनायझेशन आणि IIT चेन्नई सुद्धा. सो दे आर ऑल वर्किंग टुगेदर अँड दे हॅव RIS. RIS काय करतं बेसिकली शॉर्ट मध्ये, हा जो बीम चाललाय ना त्या कॉर्नरला, त्या कॉर्नरवर जाईल आणि त्या कॉर्नरवर एक सरफेस असते. तुम्ही काय कराल, तुम्ही त्या कॉर्नरला करून अजून एक रेडिओ लावा, टॉवरवर अजून एक रेडिओ लावा, सो इकडे बीम देईल. that is not smart solution. So what do? You place a panel over there. That panel is again a combination of small patches only. Signal त्याच्यावर जाईल स्नेल्स लॉ आपल्याला माहित आहे N1 sin theta is equal to N2 sin theta. There will be some angle of incidence and that panel is reconfigurable. Reconfigurable means it will catch the signal. Channel estimation will huge part of channel estimation will computer science algorithm खूप heavy use केला जाणार आणि ते estimate करणार की user कुठे आहे. मग त्या युजरला मला सिग्नल रिफ्लेक्ट करायचा आहे. इकडून आलेला सिग्नल तो RIS त्या युजरला रिफ्लेक्ट करणार. So that is what the future of 5G advanced and 6G. कारण आता डेटा आणि हे त्याची एक सॅच्युरेशन येऊन गेलं.
It will be located that IRS will be located in different buildings naturally available right.
आता तिथे खूप मोठा प्रॉब्लेम आहे. तुम्ही RIS इम्प्लिमेंट कसं करणार? मग जर जिओनं RIS लावला तर एअरटेल पण त्याच्यासाठी एअरटेल पण ते वापरणार का? अदरवाइज ते एक मेटल प्लेट आहे. कुठलाही आलेला सिग्नल रिफ्लेक्ट करेल. ती दुसऱ्या कोणाला डिस्टर्ब नाही करायला पाहिजे. हा एकदम म्हणजे अजून इनिशियल स्टेज मध्ये रिसर्च आहे. Nobody has implemented in the world, but this concept will 5 years down the line will be there. कारण आपल्याला असं कव्हरेज पाहिजे की कुठेही युजर असला तरी त्याला सिग्नल भेटला पाहिजे. त्याच्यासाठी RIS होईल. You can just Google RIS खूप फॅन्टास्टिक आहे. त्याच्यावरच काम चाललंय. All right then, I hope I could make some meaningful contribution throughout this almost 3 hours. जर बोलण्यामध्ये माझ्याकडून कोणाला काही बोलल्या गेलं असेल सगळ्यात पहिले मी सॉरी म्हणतो. माझं इंटेन्शन फक्त एवढंच होतं की तुमचं इकडे अटेन्शन असायला पाहिजे आणि जेणेकरून मला जे सांगायचा मी प्रयत्न करत आहे आय शुड कनेक्ट विथ यू. त्याच्यानंतर ऑफिशियली आय एम व्हेरी मच थँकफुल टू जयश्री मॅम, जया मॅम, HOD इलेक्ट्रॉनिक्स डिपार्टमेंट, कोऑर्डिनेटर कांचन मॅम, त्यांची पूर्ण टीम. चुकीनं मी सरांना म्हणजे मला तुम्हालाच बोलायचं होतं पण मी नाव त्या सरांचं घेतलं आणि हे सर पण आहेत. आणि सगळ्या लोकांनी जे मला 2-3 तास शांतपणे ऐकलं, समहाऊ जे मला थोडंफार माहित आहे आय एम ट्राईड की थोडं तुम्हाला शेअर करू. थँक्यू सो मच.
तुम्ही लाडके होते.
सर्व डिस्कनेक्ट करू कोणाला पाहिजे नाही.
On behalf of Cummins College of Engineering and this program, I am thankful to Namarti sir to deliver a very complicated and difficult topic in a comparatively simpler way and to create our interest in this area of design of power amplifier. As well as another interesting topic which was initiated by our earlier speaker. That topic we just had a discussion. Sir said that Vivek sir will explain it in better way, and he immediately accepted it that I will explain it. And after completion of his own session, original defined session, he took that topic and he completed. He showed us very interesting results from the software. So I am once again thankful to Vivek Ratnawati sir. I hope he will take us to go into the related topics some more.
Himraj, you say?
And tomorrow we are having a session at 9:30 a.m. Which is going to be taken by Professor Jayant Mukherjee from IIT Bombay. So I hope all of us will understand the level of IIT professor and आपण ज्या कॉलेजमधून आलेले आहोत आपल्या इथले सगळेजण त्याला वेळेवरती हजर राहतील याची आपण काळजी घेऊ. सगळेजण 9:30 सेशन आहे ठरलेलं त्याच्यानुसार ते सुरू होईल. 9:15 पर्यंत आपण सगळे इथे आपण येऊ.
आणि सेकंड सेशन जे आहे ते कस्तुरी मॅडमचं आहे, डॉक्टर कस्तुरी पाटील. तर ते हाफ एन आवर त्यांचं प्रेझेंटेशन राहील अँड देन शी विल बी कव्हरिंग ऑल दी हँड्स ऑन सेशन ऑन HFSS. HKSS आपल्याकडे आहे इथे इन्स्टॉल. तर त्या पूर्ण HKSS मध्ये अँटिना कसा डिझाईन करतात, फ्रॉम रेक्टँग्युलर पॅच अँटिना टू रिकॉन्फिगरेबल अँटिना, असे 2-3 ते पूर्ण एक्झाम्पल्स घेणार आहेत. तर I will request all of you to please attend all the sessions.
जेडीचे मैडम बाकीचे पण आज आलेले नाही आहेत ना, तो उनको भी आप बताइए कल टाइम पे प्रेजेंट करने के लिए.
तुमच्या कलिग्सला सांगा ज्यांनी केलं आहे ते रजिस्टर ते यायला आणि अटेंड करायला उद्याचं सेशन. आणि परवाचं सेशन जे आहे ते अनिरुद्ध कुलकर्णी सरांचं आहे. ते कम्प्लिटली हँड्स ऑन सेशन राहणार आहे. म्हणजे अँटिना फॅब्रिकेशन, त्याच्यानंतर त्याचं टेस्टिंग कसं करायचं ते, आणि पूर्ण लॉनमध्ये बाहेर ते सेशन्स घेणार आहे. आणि रडार सिस्टीम वर कसं टेस्ट करायचं, रडारचे पण ते एक्झाम्पल घेणार आहे, डेमो देणार आहे. ठीक आहे. आणि बरंच काही ते त्यांच्यासोबत कॅरी करत आहे. तर परवाचं पण सेशन करायचंच आहे है ना. आय रिक्वेस्ट ऑल ऑफ यू टू प्लीज अटेंड ऑल दी सेशन्स. नेक्स्ट म्हणजे पूर्ण सगळे सेशन्स अटेंड करावे.
Please try to come in if possible.
ओके, थँक्यू सो मच. आणि आजच्या सारखंच आपण लंच ब्रेक उद्या थोडं लवकर घेऊ आणि सेकंड सेशन लवकर चालू करू, म्हणजे आजच्या सारखं व्हायला
हो.
शकतो 5 वाजता.
Thank you.